Good morning, everyone. Today we have, this is our final day of the WHPI workshop, but not the final day of working on WHPI data together. Today we'll start out with a session. It's a focused topic on quiet time impacts on planets, and we have a number of excellent talks there. It'll be followed by a panel of people working on talking about modern minimum and long-term solar variability. So as we consider these most recent minima, we'd like to put them in context with long-term behavior of the sun. Then there'll be a number of wonderful posters. Yesterday, I think people were saying they had really good interaction at the posters, and we hope to continue that. And then we'll finish up with what we hope you will all join in for. It's plenary collaboration planning. It's where do we go from here? And so please, I hope you guys will be able to participate in all of this. We'd like to remind you, or if you haven't been here yet, we try not to post questions in the chat. If you post questions in the chat, then the answers and other questions get all messed up. There's an excellent app or website called Slido. It's easy to get to, it's easy to use, and everyone can respond to the chat if they want to. So speakers, people have questions, are encouraged to put their questions in Slido as soon as they have the question. Don't wait until the end. If you have the question, you can go ahead and put them in. And also speakers, you should be looking at Slido to give answers if you want. So if we don't have time to get to it in the discussion, you'll be able to give answers. Kelvin, did you want to give them a little more overview on using Slido? Or do you think we're good?
I think we're good, Barbara.
All right. All right, so let's see. So this is our final day. Would any of the other people on the organizing committee like to say something before we get started?
No, I think we should get going.
Great. Yep. This has been really fun. All right, so I'd like to introduce Heather Elliott and Carlos Martinez, who are the chairs of the session number 12. Heather and Carlos, take it away.
Okay. Hello.
We hear you, Heather.
Okay. Okay, I thought Carlos was gonna. Okay, so our group is working group 1, and the focus topic for today is quiet time impacts on the planets. And we have 4 speakers. We're going to save the questions at the end, so you can enter your questions into Slido. And the 4 speakers are Fang, Kai, Bernie Jackson, Daniel Gershman, and we'll see the topics as they come up. So we can get started with Fang.
So should I start?
Yes.
Okay, cool. So, so I need to share the screen. So can you see my presentation?
Yes. Yes, we see it.
Okay.
You can go full screen.
Okay, yeah, sure. Okay, so now it's in a full screen mode, right?
Yes.
Okay. Good morning. Thank you for the opportunity to let me to talk about the long-term variability in the Martian upper atmosphere. So this is the so we are care about how during the solar cycle scale, how the atmosphere is respond to the solar cycle. But apparently, because we are talking about very low altitudes, and usually this altitude at Mars is not directly affected by the solar wind. So except some very extreme ICME event, they may see some effect there, but usually there's no. So we here basically we're talking about the seasonal effect or annual effect, and then the solar evaluation. So okay, so let me just try to introduce the sun effect here, because the Mars is very different from Earth. You can see here the sun Mars distance changes a lot from the different seasons. Usually they use in the solar longitude LS. From 0 to 360, so from the equinox to the solstice to another equinox, and then to the winter solstice. So the perihelion is here at this one, and then the aphelion is here. So if we plot the sun Mars distance at the y-axis here, this is the solar longitude here. So this is shows the annual variation of the sun Mars distance changes, and then it can be very easy to using a cosine function to fit it. And then this is the inverse square of the sun Mars distance, and then we can use another cosine function to fit it. So basically, we can see that because of the sun Mars distance change a lot during the Mars year, the solar radiation reaching the Mars orbit, they if you compare the minimum and maximum, they can be dipped by about 45%. So that's a very large difference. But not just the sun Mars distance, but the solar EUV. This is very important, because for the ionosphere, for the thermosphere, also this is the direct energy input to the upper atmosphere. And then if we compare the solar EUV at Mars orbit, this is the time, and this is we compare here with three solar EUV process, f10.7, and then the MAVEN directly measured, and then another one is the time measured expiration to the Mars orbit. So we can see that if we compare, this is the sunspot number, and then we can see that the solar EUV at Mars orbit, they modulate, they have a very you can see very clear solar cycle variations, but also on top of that, there's a annual variation is modulate the solar UV intensities. So this means that if we consider the solar infrared and then the solar UV, they have they have very strong annual variation and then also solar cycle variation. But for the Mars upper atmosphere, that's not very the observation is very scarce. So this just gives you an idea of the previous observations. So usually you can see that this is the early one, and this is the current one. This is the altitude, and this is time. So at the upper atmosphere here, we are talking about, we are using MAVEN measurement here. We study the long-term variation. So first, at least altitude regions, usually there's no many observations. Another one is that the long-term variation also not available, except that they have some at 400 kilometers, that's very high altitudes, they have some observations. Yes, so we'll another thing is that most of the, you can see, if you see carefully, most of the observation is during solar minimum. So except that this early MGS and MO POD data, they cover about solar cycle worth of data. So the long-term variability, so we can make some comparison from the solar mean, because the MAVEN data usually basically in the solar mean. So we can make some comparison, altitude comparison, also the solar mean, solar max comparison. Okay, so begin we go to the MAVEN data. I just want to use in a model, theoretical model, to give us an idea of how on average, how is the Mars atmosphere variation changes. So this is the y-axis is the altitude, and then x-axis is the solar zenith angle. So this is averaged, and during the quiet time, and a different panel for the different species. So we can see that basically the average behavior for the Mars atmosphere is very solar zenith angle dependence is very smooth on the day side, but there's a large day-night asymmetry. And particularly for the terminator, there are some big changes. So because this study is for the data analysis, we try to minimize the data bias. So we focus on the day side because the smooth solar angle dependence, and also we can avoid the night side. Okay. And we see that there are some solar angle dependence, so we need to try to remove that, because we consider the whole day side as a whole. We try to understand the average behavior of the day side atmosphere. So I won't go into the details of here, but basically we find that for the different species, and then for the different seasons, different solar longitude ranges, and then for different altitudes, we doing some fit, the density versus the solar angle fit. Then we using that fit to scale each all the day side observation to the 60 degree here. And this is give you an idea how the solar angle fit works. So the left side is the at altitude near 180 kilometers, and then for the CO2 argon N2NO, and this is the before solar angle. Oh, sorry, this is before, and the right column is the after. So we can see that after the doing the scaling, because we particularly for this one, this is not this is purely because the solar angle is very different. Not because we check the dust activity, we check the longitude, latitude, everything, but only the solar angle can expand that. And after we doing the solar angle scaling, we find that the data, this kind of the anomaly disappeared or minimized here. So this shows that solar angle is very important. And another one is that from this one, we find that the solar angle dependence of the scaling is very important near the perihelion, when the sun mass distance is the shortest, and then is less pressing for the aphelion, because you can see that the slope is very flat near the aphelion, but it's very deep, steep for the perihelion. Okay, so this is the after we doing the scaling, solar angle scaling. This is the overview. The altitude versus time, the color coded by the densities, CO2, argon, N2NO, and the top panel here give the context of the external conditions. The red curve shows the inverse square of the sun mass distance. So this gives you an idea of the on average the solar irradiation at the top of the Mars atmosphere. So how it changes with the season. So the different mass years. So the maximum at the perihelion and minimum at the aphelion. And then these curves give the EUV process. But basically we are using the f10.7 shown as the red here. And then another one we show the atmospheric dust loading.
2 minutes left.
Okay. Okay. So because here, because we noticed that there's no much day side coverage for the Maven during the dust seasons. This is the global dust storm. So because we try to remove the potential bias, so we in this study we does not consider the dust storm activities. Okay, so we doing the multiple linear regression to the 27-day average densities, because we try to avoid the solar radiation, solar rotation effects, and then the longitudinal structure due to the tidal effects. So we're doing using the 27-day average densities, and then we made the density fit to the inverse square of the sun mass distance. So this is give you an idea of the solar infrared and the Mars, but this is the indirect effect because we are talking about very high altitudes in the upper atmosphere. So but solar infrared, they penetrate almost deposit energy very low altitude in the middle atmosphere. So this is like the upward covering, because we're talking about these altitudes, and the solar infrared, this is the about indirect effect. And then for the solar UV effect, this is the direct effect, because the atmosphere directly absorb solar UV in these regions. Then we make this fit, and then we can see that this kind of the multiple linear regression pretty good capture the long-term variation here. So okay, so I won't go here, but basically we're using the statistical method called the dominance analysis, trying to determine the relative importance of the variables, the the orbital effects and then the solar UV effect to the variance of the densities. Okay, so this is the result here. So this is the regular correlation coefficient for the CO2. And then this is the when we using the statistical method, we can extract the relative importance. So this is the combined effects. They can how many percentage they can extend the variance of the densities, CO2 densities. And this is we can partition into the variation due to the F10.7. This is the solar UV effects, and this is the orbital effect. Okay, so this is all the species here. So I don't have time to describe that one. And then okay, then because this is the main data, we are limited to low altitudes, but we have as I mentioned, they have some earlier study. They are at about 400 kilometers. That's using the MGSNMO POD data. So we're using our technique to derive the relative contribution.
Okay, we need to move to the conclusions.
Okay. Do I have time to read my conclusion here, or I can leave here?
Let's move on to the next stop.
Okay.
Go ahead, Heather. Can you introduce the next speaker?
Yes. Yeah, the next speaker is Kai, and the topic is variations in the thermosphere composition and ionosphere total electron content under geomagnetically quiet conditions at solar minimum.
Hi, so can you hear me and see my shared screen?
Yes, it looks good. Thank you.
Okay, yeah. Okay, so hello everyone. So it's an honor to present my result here. Okay, so first I would like to say something about the ionosphere, the Q disturbance. So the Q disturbance is the variation of the ionosphere parameters due to the Earth's atmosphere itself, not from outside of the Earth. And it was first studied in the 1978 by the Devenica and Hill. They used one ionosound over the St. Jude's, but still to study. Then there are many studies focusing on the Q disturbance provided by the ionosound since they are pioneering work. And so in the 2004, the Mikhailov summarized the latitudinal and the seasonal variations of the ionosphere Q disturbance. And here I show you an example. And so they use the 27-day average to as the reference value, and show in the dotted line, and for the solid line, it is the corresponding Q disturbance. And as you can see, for the Q disturbance, they can be either depletion or the enhancement, and it can happen both in the day and in the night. However, the many so-called Q disturbance, they are under the geomagnetic quiet time. They are actually still influenced by the geomagnetic activities. The observed results shall be the joint effort by the low atmosphere forcing and geomagnetic activities. So in one of my paper accepted last year, we find that for the weak geomagnetic activity, it can still generate long and strong response in the column density ratio of the O2 and 2 in the mid and high latitude during the solar mean. So here we pick 3 examples, and as you can see, when we calculate the percentage difference between the disturbed day and the quiet day, there appears a large area of the depletion, although it is only a snapshot, but actually this continuing time is all longer than 10 hours. And in the middle column for this case, the KP max is only 2.2. The KP max is only 2.3. So then now we make the rules stricter to set the AE less than 250 for the whole day and KP max less than 2 to see what happens for the O2N2 and TEC. And here we find an example. So from the day 109 to the day 112 in 2019. So as you can see, during these 3 days, the AE are mostly less than 250, while the KP max is only 1.7. So this period can naturally be regarded as the quiet period. However, when we calculate the percentage difference of the O2N2 between the day 111 and the day 1110, we find that there appeared a localized depletions in the mid-high altitude. And as for the TEC, we also find some depletions in the almost similar geographic range. And then we also run the TI-GCM, we're driving with the warmer, but the lower boundary is just the tidal climatology, no tidal day-to-day variability. Then we find that the model can reproduce the observed depletions to some extent. However, when we run the model again by removing the geomagnetic activity, the result, the variation is pretty much weak. So to uncover how the depletion is formed, we also provide the temporal evolution of the O2N2 variation before the gold observation. By the way, so although this only a snapshot, but actually this depletion continued from the 1110 to the 2110, 10 hours. So here for the variations before the gold observation, we find that there's already a depletion formed in the beginning of the day, and then it was transported equatorward and westward. So from this, it looks like the behavior is pretty similar to the O2N2 response to the storm. Yeah. So then we also give a preliminary analysis to see whether the low atmosphere forcing can make major contributions. So for the tides, they are based on previous studies, they are mostly in the lower altitude, where we are here, we are in the mid-high latitude. For the gravity waves, based on the VEDAS 2007, the waves that can reach the middle thermosphere are mostly high frequency, less than 1 hour, while here our observation is 10 hours. Then for the planetary waves, based on the previous studies, the O2N2 variation due to the planetary waves is only 5 to 6%. It's much weaker than our maximum 30% here. So based on this primary analysis, it seems that the low atmosphere forcing cannot make major contribution to the variations. And furthermore, the solar F10.7 is also constant here. So therefore, now we can see that the minor geomagnetic activity during the quiet period is it's the most likely the major contributions. So in summary, during some magnetically quiet periods, the gold observed strong localized daytime O2N2 variations at the mid altitudes, and for the corresponding ionosphere TEC, there's also the depletions seen in the region of the O2N2 depletion. And for the model simulation shows that the minor geomagnetic activity can play the crucial roles sometimes in this quiet time variations. Thank you so much. Yeah.
Okay, well, thank you, Kai. I think we're going to do the questions at the end of the session, and so for right now we are going to move on to the next speaker, which is Bernie Jackson, and the title of his presentation is UCSD Iterative Interplanetary Scintillation Analysis during the Bepi-Colombo Solar Orbiter Venus Close Pass. So he's going to look at the interaction at Venus. So looks like he's getting his presentation up.
Is it up now?
Yes, we can see it. If you could go into presenter view.
Will do.
And we can hear you too.
Okay. I'm going to talk about the Bepi-Colombo Solar Orbiter Venus close pass that just occurred last month. Actually, at Venus, there's Bepi-Colombo. So there were Bepi-Colombo Solar Orbiter and the Japanese Akatsuka Venus probe orbiting at the time. And so there are quite a few interesting observations that can be obtained from all of these spacecraft. I'm going to talk about, but mostly I'm going to talk about our contribution, which is the interplanetary scintillation analysis of the solar wind and the reconstruction of it at this period. We have predictions and the differences between predictions and forecasts. I'm going to show you both and the current progress we have in providing measurements at different locations. And then I'll continue. Anyway, here's what happened during the Bepi-Colombo close pass. Now, both Bepi-Colombo and solar orb. This is Venus, and both Bepi-Colombo and Venus are there. You don't see much differentiation, but you surely do see the solar wind effects at the time. This is Bepi-Colombo, this is orbiter, and here is Venus on its orbit. Now, Venus is on its way at this, or Bepi-Colombo here is on its way to Mercury, which is right over here and this is sort of a broad view, but this is the view we get in the ecliptic plane of these systems. Now, over on the right, you see what happened. Orbiter first passed Venus on 9th August on its way to orbit the sun at higher latitudes. Bepi-Colombo went by on August 10th, and this is a depiction over on the left of the various instruments on board Solar Orbiter. This is the magnetometer, this arm that sticks out here, and this measures magnetic field in the interplanetary medium. The other instrument of interest are for us, are the plasma analyzers here and here on Solar Orbiter. Bepi-Colombo is an instrument that's hidden behind this sun shield. The Japanese call this NEO, and there's an interesting story behind that. It has a magnetometer that you see sticking out here. It's also shown here, and that measures the magnetic field as well as Orbiter does at this time. And then, of course, the Japanese spacecraft is viewing Venus in orbit around Venus, and it has taken pictures of this sort of the Venus surface. It's a very interesting system of imagery that can show the cloud cover of Venus. This is a depiction from Orbiter of what happened during the close pass. You can see, yep, it went by and very close to Venus. Now, our instruments, the way we do this is interplanetary scintillation, and in Japan, a system of 3 radio antennas that view the solar wind, and this is one of them near Mount Fuji. You can put all these data together and get from the system and get a 3D reconstruction like I showed first off in this talk. That's a forecast web page. And what we have on the forecast web page now is of the prediction of all the inner planets and spacecraft that are of interest here. You can see a lot of places where we've extracted the solar wind parameters. Here's density and here's velocity. And we go up to the current time that this was taken and then show a forecast of what's happening a few days in advance for each one of the instruments that's present. Sorry, for density and velocity that's present at the spacecraft from our system. It's kind of hard to see this on a website, so we have a place that you can hover over things and look at, for instance, what Bepi Colombo is showing. And this was back at last Thursday when I gave this talk to the group. Today, though, you can see what's happening with Bepi Colombo and Mercury. Bepi Colombo, of course, passed Venus on its way to Mercury, and it's going to be passing there for the first time early next month. Here's Bepi Colombo and here's Mercury at this time, and Earth is over here on its orbit. And these are all the inner planets that are present. We also had magnetic field, and we extract this from the system, and you can see this in radial and tangential components over on the left at the location of all the planets. I showed you this before, and this again illustrates what's happening. There's always solar wind. It's interesting. Here's Parker Solar Probe coming around near the sun, and it comes out and goes past, while these two planets are pretty much close to the planet Venus. And at this time, Parker Solar Probe is pretty well aligned with stereo. So probably interest to us is the fact that you can see structure at Parker Solar Probe that also will a few days later get out to Venus. I'll talk more about that. Here are depictions, animations of the whole time during the solar orbiter and Bepi Colombo close pass of Mercury, of Venus, sorry. And here you can see density in an ecliptic plot. This is density in a meridional plot through Earth, showing all this different spacecraft. You could make a meridional cut anywhere you want. So you could also put one through Venus or Bepi Colombo. You have command of the 3D volumes here pretty much. These are the magnetic fields in radial component, tangential component, and these are, as you see here, this is velocity, determined through the interplanetary scintillation analyses. This is this you see is from yeah. Let's see. This is anyway. These are at the different spacecraft here, really tangential and radial magnetic fields. And you can sort this out, and it's quite well presented. Let me go on here. But it kind of makes you a little leery seeing all those animations at once. We do better. We can forecast these things. We do better in archival mode, where we have all the data available and can reproduce structures. And so here you see density at Venus and Bepi Colombo. Venus and Bepi velocity. Down below here is velocity at Venus and Bepi Colombo. here is radial magnetic field at Venus and Bepi-Colombo over this 1 month period that we were able to reconstruct, and magnetic tangential magnetic field on the lower right-hand corner. Like I said, I took, here's the Bepi-Colombo closest approach at this time. And so all spacecraft make just a blob here at the location of Venus. Here, the Parker Solar Probe and Venus are radially aligned. So you can see structures here at Parker's that are present at Parker Solar Probe, and that in about 3 days arrive at
Okay, Bernie,
Venus.
you've got like one minute to wrap up.
And here are the same 3 depictions of radial magnetic field at this time. And in conclusion, we have these data. We have very much interesting material that we can use to compare with Bepi-Colombo Solar Orbiter or others, and the groups that are analyzing the in situ data at these times. Thanks.
Okay, Bernie, thank you. We are gonna do questions at the end.
Okay.
So our next speaker is gonna be Dan Gershman, and the title of his talk is Quiet Sun, Planetary Magnetospheres. And please do enter questions into Slido, and we're gonna do questions for all 4 talks at this.
Dan, you'll just need to switch displays. Just click the button in the center there.
Yes.
There we go. We can see it perfectly now.
Okay, got it.
And
All right.
I think we need you. Okay, yes, good. You've unmuted. Thank you.
Great. All right, so morning, everybody, and thank you for having me as part of this session. And so really wanted to just talk through kind of at a high level what talk at a high level kind of what's going on in the solar system with the different magnetospheres. And so I don't really have time to do a deep dive into all of them, but just kind of talk about what's happening sort of in a broad sense at the different magnetospheres and how they might change sort of during a quiet sun or solar minimum condition. And so the thing to think about here is essentially what is driving a magnetosphere. And it's essentially a competition between 2 sets of forces. One is the external forcing from the solar wind, and then internal forcing, which is planetary rotation, and also internal sources of plasma in the planet. And so some of the planetary magnetospheres are filled with more solar wind plasma, and some have their own sources that help drive dynamics. And so it's important to understand and think about at each of the different planets under different solar cycle conditions, what's actually dominating and what's controlling the physics of the magnetosphere and the transport of mass and energy throughout the system. And so one thing that we looked, Gina DeBraccio and I looked at recently when trying to understand kind of solar cycle variations of what's happening at the outer planets, we kind of looked at the whole heliosphere as a function of solar cycle. And so we put together this plot here, which looks at dynamic pressure, which is the top plot, magnetic pressure, which is the second plot, and alphanic Mach number, as a function of essentially heliospheric distance, and convolved in that based on when different spacecraft actually sampled those heliospheric distances, convolved in that is sort of solar cycle effects. And so if you look at what is happening as Voyager, for example, moved out throughout the heliosphere, it was the only spacecraft that was measuring there. So some of these wiggles that you see in the outer heliosphere are actually a measure of the solar cycle and solar activity. So you actually see how the outer heliosphere responds to that. So a few things to mention here. One, if you look at the solar wind dynamic pressure, you see it's actually pretty flat, scaled to 1/r². And you don't really see big solar cycle effects here, which is essentially saying that the dynamic pressure of the solar wind's not changing too much as a function of how many sunspots there are. The magnetic pressure, however, you see does have these variations with solar cycle. That's because you have CMEs coming out from the sun, adding sort of the total magnetic flux to the solar system. So it pumps up the entire magnetic field throughout the entire heliosphere. And that's important because when you combine these two quantities to get Alfvénic Mach number, it turns out that upstream Alfvénic Mach number to magnetosphere is really important for telling you kind of roughly how much magnetic reconnection can probably happen at the magnetopods. And there's some studies of this and some different ways to think about this, but kind of a magic number you can keep in your head is about 8. And so if you have an Alfvénic Mach number below 8, you can get a decent amount of increase of magnetic positive reconnection. When it's over 8, you tend to have less. What you can see instantly here is that Earth, it's sort of about 50-50, which is why you see sort of this, half the time you get good magnetic reconnection during southward IMF and half the time during northward IMF you don't. What you can see throughout the heliosphere is that in the inner solar system where you have, for example, Mercury, the Alfvénic Mach number is always below 8, doesn't matter what phase of the solar cycle you're in. So that can tell you that reconnection is going to be really important, and there's going to be a strong coupling between that magnetosphere and the solar wind. And as you get to the outer solar system, you can see that the Alfvénic Mach number is pretty high, and at places like Jupiter and Saturn, you're probably not going to really care what the solar wind's doing too much. And at places, and there are some solar cycle effects here. And so as you get increased solar activity, the Alfvénic Mach number goes down. So as we talk about quiet sun, we're talking about a higher Alfvénic Mach number. So a quiet sun would tend to reduce the overall interaction between the solar wind and a magnetosphere. And so really what I want to just do for the rest of the time is just kind of go through the different kind of types of magnetospheres at a high level and what might be happening. So we'll start with Mercury. As I said, the Alfvénic Mach number, even during those solar minimum conditions, is pretty much always below 8. And there's really no internal plasma source at Mercury that is kind of driving dynamics. It's really at the mercy of the solar wind all the time. And so if you look at this little cartoon down here, if you look at the Dungy cycle and the scale at which plasma can kind of recycle around the whole Mercury system, instead of, on the hour time scales at Earth, we're talking a couple minutes. And so Mercy is essentially at the mercy of the solar wind all of the time, even during quiet sun conditions. And it'll respond very quickly to what the solar wind is doing almost instantaneously. And so if a high speed stream comes out from a coronal hole, during the solar minimum, Mercury will respond to that within a couple minutes. And the whole Dungy cycle is just faster, so plasma circulating about an order of magnitude faster at Mercury than at Earth. The other extreme of that is the gas giant magnetospheres of Jupiter and Saturn. Here, these have, not only is the Mach number high during solar minimum, but you have such tremendous sources of plasma inside these magnetospheres. So from the moons, Io and Enceladus, and Jupiter and Saturn respectively, you just have most of the mass of the magnetosphere coming from internal sources. And so you have a really rotationally dominated system. And so sure, the solar wind might push on it and squeeze it and squish it a little bit because the magnetospheres are just a little squishier because of all this internal plasma. Ultimately, especially during quiet sun conditions, you're really seeing a rotationally dominated environment, and there's not a huge amount the solar wind can really do to impact that system. And then finally, that leads us to the ice giant magnetospheres of Uranus and Neptune. And these are really interesting because of a few reasons. One, they're further out than Jupiter and Saturn, but there's no strong internal sources of plasma. So in some ways, it really is dominated by a lot of solar wind plasma. The other really interesting thing is that you have these highly tilted axes, both the rotational axis with respect to sort of the out of the ecliptic, and also the magnetic axis with respect to the rotation axis. And you get some really interesting geometries as the planets rotate and some interesting seasonal effects. But let's take the example during solar minimum quiet sun, where you have a really high alphatic Mach number. Ultimately, that turns to limit the amount of reconnection that you can get at the magnetopods of these planets, even when the magnetic field's doing some interesting things. That being said, because you have these highly tilted rotational and magnetic dipole axes, just the way in which the convection electric fields in the plasma can transport around this system is fundamentally limited, as opposed to you don't necessarily get like a closed plasma sphere as you might get at Earth. And so there's theory from Vasiliunas, an early paper now in the Voyager era, that really argues that these planets must be solar wind driven, really under any condition, because that's just the only thing that can truly drive them effectively. And so it's really an open question on exactly what these planets are doing. There's now some increased, as we think about actually visiting these planets again, increased interest in studying these, but it's really an open question. But ultimately, it may be that the planets that are furthest out, even than Saturn and Jupiter, still are actually pretty dependent on what the solar wind is doing in terms of driving that mass and energy transport. And so I'll essentially finish there. The upstream Mach numbers are a great way to think about the interaction between planetary magnetosphere and the solar wind. And ultimately, the Jupiter and Saturn are the most weakly driven. And what's kind of interesting is the planets closest to the sun and the planets furthest from the sun may be actually very strongly driven by the solar wind, even during quiet sun conditions. And of course, there's lots to learn about Uranus and Neptune, which is why, of course, we want to actually visit those and collect that kind of data. So I'm going to finish there. Thank you.
Okay, thank you. Okay, so we're going to be transitioning over to our question discussion section for these 4 talks.
Yep. Thank you, Heather.
Okay.
Let's start. First of all, sorry for the abrupt interruption. So I was a bit concerned about timing. So you have a chance to say a few words about the summary of your work, and then we can jump to the questions. Sarah, you have a question, so go ahead, please.
Okay, so
Yeah.
should I,
Oh, sorry, yeah, so actually my question was a leading question for you to give a chance to say something about your conclusions, and in particular, can you say something more about how you separate orbital and solar EUV effects? Is it easier?
Okay, so basically, I just doing the statistical analysis. We're doing the multiple linear regression between the density and then the 2 terms. One is the 1 over r square, another one is the f10.7, because for the mass is different from Earth, because the 1 over r square they regulate everything, right? The submass distance regulate the solar radiation at top of Mars atmosphere, but the solar EUV also depend on the solar activity. So, but if we do, I know these 2 terms are correlated each other. But if we consider that the solar, if we're trying to separate the density variation into 2 parts, one is due to the solar infrared, another one is due to the solar EUV. We can see that solar infrared at Mars is about just regulated by the 1 over r square, because the solar infrared, because we talk about the density variation, is by many factor, affected by several times. So this density variation is much larger than the solar infrared changes. Okay, so basically we can consider the solar infrared as sun is stable from the Mars atmospheric perspective. So if we consider the separate the solar infrared and solar EUV, so solar infrared is just regulated by 1 over r square, and solar EUV, they not only just 1 over r square, but also the solar activity. Okay, so this is the reason. So although we in our linear regression, we just doing the correlation to the 1 over r square and then the f10.7, but I interpret this correlation as the correlation to the solar infrared and then the solar EUV. Because the solar EUV effects has been included in the f10.7 terms.
Thank you. And now you're here, Sarah. Can you go ahead with the next question?
Yeah, it's related. And of course, we don't have a lot of time, so I didn't quite catch. You were talking about, I was talking, oh yes, good, you've got it up there. The colors on your slide, and you had a slide about density scaling with, I think it's solar zenith angle, is that SCA? Were they different positions, different times of the solar cycle? What were you mentioned that and I didn't quite catch it.
Should I share my screen so that
yeah, if that's all right with the chairs, I think it might be helpful just to look at the figure.
Yes.
Okay. So can you see my screen?
Yeah.
Okay, so you are talking about this one, right? Am I right?
That's right.
Okay, so I'm sorry, I didn't have time to, and I also recognize I didn't put the here. So the different color here for this one, this is for the different Martian year. So because we find that for the different Martian year, because the solar cycle variations, the slope are a little bit different. So we separate. For example, for this one, this is for the CO2, and this is for one season near the equinox and then at one altitudes. But we also separate into so with our parametric space is including the altitude, season, and then the Martian year. So for that one, we separate, we derive the solar zenith angle dependence, and then we use that one to scale each individual data point. And this one, this just solar zenith angle. This just shows that okay, the anomaly here. This just because this one is more closer to the subsolar point. So this is the reason why after we doing the solar zenith angle scaling, we to the 60-degree solar zenith angle, we reduce the density here. So I try to say that okay, the solar zenith angle affect the density difference, but trying to in our doing the long-term variation, we need to remove this variation, the sampling difference from our long-term, really, I mean the true long-term variation.
Thank you.
Okay, thank you. I think the next question will be from Ian. If we can put the slide back in. Sure, can you stop sharing? Great.
Okay,
Ian,
thank you. So Xiaohua, that was very interesting talk. You did mention the dust storms. It's something I've been wondering about. Could you talk a little bit more about them? Are they seasonal? Do they follow some pattern? And how much do we need to be aware of the dust storms when we're looking at Mars?
Okay. I would also like to just share my screen. So if can I share my screen?
Yeah, great.
Okay. Yeah, so this is the dust storm. So can you see my screen here?
Yes.
So okay, so this is the optical depth, the dust storm of optical depth. So this is like the policy of the atmospheric dust loading in the atmosphere, but this is in the lower atmosphere. This is okay. So the different panel just for the different Martian year from 24 to 34, and then this is the season from the 0 degree to 360. And then, so basically, you can see that this is the season when the dust activity particularly severe. Okay, then this is the recently, I think this is the global dust storm. So yes, the dust storm activity is very seasonal, and particularly near perihelion. But there are some reasons we neglect the dust activity because of, first, the dust particles, they found that they cannot expand to very high altitude. Usually they limited by the 80 kilometer. So the direct dust particle aerosol heating is usually very low. So the dust activity they can affect the atmosphere, but less affecting is the indirect effect. This is through the coupling effects. So if you heat the lower atmosphere, so they just the atmospheric expansion and contraction, so they can affect the sometimes they can see at the upper atmosphere and even go to the magnetosphere. But that is unclear how long the dust activity can exist. And then another one is that previous studies like the Jeff Bobs, they found that there's no very clear correlation between the dark activity at 400 kilometers with the densities. Another one is that when we see the here, so can you see?
Yes.
So basically, if you okay, the brown here, this is the dust activity, this is the dust loading. Okay, and then the red one is the 1 over r squared. So this is regular the solar radiation infrared, and this is the blue one. For example, this is f10.7. So we can see that the high dust activity usually happens for the perihelion here, but when the peak of the dust activity usually happen, they coincide. I'm not sure whether this is the physics or just coincide, but because they happen near the perihelion, so you can see that the peak of the dust activity usually happen either in at the peak of the f10.7 or peak at the solar infrared peak. So this is the reason why it's very hard to disentangle the dust activity with because there's some correlation here.
Yeah.
Another one is that our correlation, if we negate the dust activity, we still get a very strong correlation. So just using the 1 over r squared and then f10.7, we can explain about 80% of the density variation. So this means that even dust activity is important at high altitudes, less contribution show less than 20%.
Okay.
So the dust activity is not very strong signature that we can say that dust activity is the primary. Even existing, it should be the secondary, and then the dust activity should not be very strong because we are talking about the long-term variation. The dust activity, they can see at high altitudes, but because we are using the 27 data averages, and it's not clear how dust activity perturbation can be seen in the long-term changes of the atmosphere.
Okay, thank you. We need to
Great.
move on. Next
Thank you.
question. Is Sarah, you again for Shuguang?
Sure. Can we pop that back up?
Yes.
Okay, so I think this was the question about, oh yeah, I was just wondering about which periods you've done the gold TICGM analyses. As we're starting to do some collaborative work on WHPI, how hard is it to do similar analyses for different periods of time? And just a sense of what the scope is time-wise and what's been done with the gold model comparisons. Is Shuguang there?
You might be muted.
Is he not?
Okay.
He's still here.
Okay.
Sorry, Shuguang, if you've been talking, we haven't heard it. Maybe we can come back to that, Carlos?
Okay, yes. So let's jump to Bernie. You're again, Sarah.
Bernie, oh yeah, that was really interesting. And I actually have a broader question, which has to do with, how continuous are the observations that you're getting? You're showing us these wonderful observations of different spacecraft and where they fit in what you're modeling in terms of the heliosphere. So my question is, in the specific, that image you saw, was that the heliospheric imager? And then a little bit more generally, if we saw CME tomorrow, would there be data available from all those missions that you pointed to?
The image you saw of Venus was one from the Akatsuka spacecraft, but that was a long time ago. They're able to do that quite regularly, and so they obtain that and get information about the cloud cover of Venus. And with numerous imagers on their spacecraft. But what is of interest in our analysis are the plasma monitors and magnetometers on the instrument. And as you saw at the actual passage of Venus by both of those, both Orbiter and Bepi Colombo, we we didn't see, it was about as quiet as you could expect as far as the solar wind was concerned. So that may factor into this. We'd surely like to know what the various monitors are showing, and those monitors on orbiter are the plasma monitors and the magnetometer. And so when I show the magnetic field, you can compare what we see with the magnetometers on the spacecraft. They're still calibrating the instruments, and we're still trying to figure out how well we do, because we really only have good comparisons at Earth currently. And we're not so sure about those even. The Bepi Colombo gives has magnetometers too, and those are on all of the time supposedly, and still being calibrated. But we should hear more about that. There's a meeting at the end of this month, and it's specifically designed to describe the various instruments on Bepi Colombo at during the Venus Close Pass. Of course, they're all excited right now because the Mercury Close Pass is going to happen at early next month, and so this is the first time and the second, basically the second spacecraft that is intended to study Mercury in detail, and it passes and makes some 6 passes before it actually goes into orbit in 2025. Then the shield, the 2 spacecraft separate. They can study the magnetosphere of Mercury different ways, and they are able to do results from both instruments, all of the instruments on the spacecraft at that time. Right now, the MEO spacecraft of JAXA is hampered a little by the heat shield that's present around it. So not all the instruments can actually do data analysis at this moment. The one I've been most interested in is PICAM, which is a plasma monitor that has a directional capability to determine where on Mercury various constituents of the plasma are ejected from.
Okay, thank you. Mm-hmm. So let's jump to a question from Janet for Daniel. If we have time, we'll go through the other questions. So Janet, please, can you unmute yourself?
Mm-hmm. Janet, you might need to raise your hand.
Yes.
There we go. Thank you.
Okay. Really interesting overview from Daniel. What always kind of bothers me, though, is that we're so thin on outer solar systems or outer heliosphere measurements that we're trying to cobble together. And to some extent, the IMAP community is confronting this in their effort to model what they're seeing and understand the whole system. Should we be doing more in the area of combining forces with this outer solar system, outer heliosphere community to extend our reach beyond Mars, beyond Jupiter, even to really get a handle on the physics of the solar wind, which changes pretty drastically when you start adding the neutral solar wind and the pickup ions and kinetic effects and so forth. What do you think about the fact that we kind of gloss over that? Should we be doing more?
That's a really interesting question, Jen. I appreciate that. I admit I haven't thought too much about it. And I would say my gut reaction is that, the good news about the Voyager data is that we actually do have quite a good amount of data kind of between 5 AU and 30 AU that tell us a little bit about what the solar wind's doing. And I would say that I from memory, and again, I haven't looked at this in a while, the pickup ions, and I think a lot of the sort of the slowing down of that solar wind from, you know, supersonic, sonic, of course, happens a lot later out. So I'm wondering if at 30 AU, it's less of a issue, although, you know, there's lots of interesting work done on sort of the effect of neutrals on magnetic reconnection. And I think getting good data out there to actually understand how CIRs develop and really what the solar wind looks like, I think is absolutely worthwhile doing. Whether that's enough to sort of break, you know, an MHD-like description at Uranus and Neptune, I'm not sure, but I think that's a really interesting thing to think about.
Okay,
Okay.
thanks. Thank you.
Thank you. So time is over for this session. Remember that you can still ask questions on Slido, and they will be answered. So let's move on to the next session. Juliana, Lien, please.
Thank you, Carlos. Welcome everyone to section 13. This is the section on the Maunder minimum panel, and Ling and I are the co-chair. Just a few words on how we plan to run the panel. We have identified some broad questions for the panel. Kevin, if you can share the slide with the question, thank you very much. So we will ask the question to the panel, let the panel reply, and then after each question, we'll open to everyone for follow-up question or comments. And as always, you can either raise your hand or you can put your question in Slido. And before we start, I would like to thank our expert for accepting our invitation and being on the panel. And I would like to go over the panelists so they can say a few words and introduce themselves. Natalie, if you want to go first.
Hello. You might unmute yourself.
Sorry. Yep. Hello, everyone. I'm Natalie Krova from the Max Planck Institute for Solar System Research in Germany. My main interest understanding the physics and the solar mechanisms and modeling the solar irradiance variability, and also reconstructions of past solar activity and variability.
Thank you. Judith.
Hello, my name is Judith Lean. I work at LASK now, retired from the Naval Research Lab, and my interest is reconstructing historical variations of solar irradiance and also actually the present and future estimates, and using these estimates to understand how the solar forcing has changed over time relative to other climate forcings.
Leif.
Yeah, my name is Leif Svalgaard. I work at Stanford University, and my interest is magnetic fields on the sun, in space, on the Earth, and everywhere actually, and how these fields connect and interact with each other.
Ilya?
I think you're muted. You can go ahead and unmute.
We can see you. Oops, seems like he's having trouble. Hanli, why don't you go first and see if we can unmute Ilya.
Okay, my name is Hanli Liu. I'm a scientist working at NCAR HAO, and my work is mainly on the atmosphere dynamics, wave dynamics, and coupling of different atmosphere regions. Also, I'm involved in developing the tool to study that, which is we use the whole atmosphere community climate model, WHPI-X.
Okay, thanks for letting me unmute myself. I am Ilya Ososkin, working at the University of Oulu in northern Finland, and I'm mostly interested in solar physics, cosmic ray variability, and their terrestrial effects.
And Matthias.
I'm Matthias Rempel. I'm a scientist at HAO, and I'm primarily working on radiation MHD models of the solar atmosphere, and I am interested in pretty much anything from quiet to active sun.
Thank you very much, and thank you for being here today with us. So let's start with the first question. We try to attach some name to the question, but every member of the panel is welcome to comment on this. So this is primarily for Ilya and Leif, that are experts on reconstructing the solar activity record back in time. And so we would like from them a brief report on the recent progress on the reconstruction of sunspot number and other solar activity indices, and how close we are to get a consensus within the community. What are the challenges and the data uncertainty that we need to overcome in order to reconstruct the record back in time? And what is the way forward?
Okay, can I share my screen maybe? Let me see.
Yes, you're a co-host. You should be able to share.
Okay, does that show?
Yes, we can see it. You can go full screen if you like.
Okay, let me see, how do I do that?
You can click where it says slideshow, and next you'll click from where it says start from beginning.
I don't really need to go full screen, but I would like to actually see the
Slideshow is at the top center above where you have the observatory image.
yeah, that's it. Well, can everybody see the whole screen?
Yes.
Yeah, okay, that's all that we need. I'm going to talk about reconstructing solar activity, sunspot numbers, and sunspot group numbers. And the interesting thing here is that we are actually beginning to understand the complicated physics of this whole system. And on this slide, I show, of course, all the things that derive from solar magnetism: TSI, EUV, flares, sunspots, solar wind, and CMEs. And these things in turn have effects, cosmic rays, geomagnetic activity, climate maybe, space weather, and so on. And so all of these things at the bottom of the figure are caused by the top. And so we can actually use them to maybe validate what solar magnetism might be. And this was actually realized a long time ago by Michael Faraday back in 1852. And so let's begin to look at this one in particular, how the daily variation depends of the geomagnetic field depends on solar magnetism. And the relationship is quite complex, but is exceedingly well understood. So solar magnetism gives us sunspot number, EUV, and that hits us, and due to the solar scenic angle, we have day and night sessions. And we also have thermal winds, where the ionosphere is blowing across the magnetic field of the Earth. And all of that gives rise to a current in the ionosphere, and that current has a magnetic effect on the ground. And this one we can actually see, and I've indicated here some time ranges. We have 410 plus observations of sunspot numbers, 75 years of F10.7, and 280 years of this. And that's because this guy here, George Graham, way back in 1722, discovered that the direction of a compass needle varies during the day. So here's a modern variation of that. So it's at nighttime, it points, let's say, to north. And then as the sun rises, the needle deviates to the east. And when the sun begins to set again, it deviates to the west, and at night we're back to where we were. So there's a daily variation of that, and it's fairly big. It's about 1/10 of a degree, or 1/6 of a degree actually. So it is easily measured. And we actually have those measurements all the way back to 1740 at least, on a regular basis. And so here we can actually show how that deviation of the geomagnetic field varies, and with the 10.7 microwave flux, that's the red, and the EUV, that's the blue. And you can see there's almost perfect correlation. These are yearly values, and it's rare to see coefficients of determination that high, but there they are. And we can actually go back in time, because we have these variations, as I said, for 280 years. And so here we are back to 1740, and you can see very clearly the sunspot cycle. So the next one. So, but that's not the only place where we see an influence of the sun. Also around the Earth in the magnetosphere, there are electrical currents, and these currents, there are actually several of them, also have an influence on the variation of the geomagnetic field. And we can construct indices going back at least to the 1840s that allows us to infer the interplanetary field measured at Earth, just outside the magnetosphere. And this used to be a little bit of controversial, but it is no longer. There is consensus now. And so we can actually figure out what the interplanetary magnetic field, what the magnitude of that has been back to the 1840s. And you see here two reconstructions that basically agree very nicely. And up here are those, that curve here is observed by spacecraft.
Like if you can wrap up, I think this is a very good point to show the agreement. I want to make sure he has a chance to give her point of view.
Well, we'll get to that. Okay, I'll not take up too much time, so let me continue. So we can now combine the magnetic field from out in space, from the geomagnetic measurements, and we have two. Here we have the red, which was from the current in the magnetosphere, and the blue, which is from the current in the ionosphere, and they agree nicely here back to 1840. What is of interest is that the field does not go to zero at solar minimum, but actually has a basal floor here. And so we can now go to a little bit more into the physics. We have satellites in space now. MDI and HMI measures the magnetic flux, and we can compute or get the magnetic flux over the whole surface, of actually over the visible disk. And that turns out to be related to the number of sunspot groups, and we see a very nice relationship here. And we can actually go a little bit further, because we also have Mount Wilson Observatory and the WSO, the Wilcox Solar Observatory, from which we can get the magnetic flux. And so there's a very nice strict relationship between the group number and the magnetic flux, which is very nice. So go to the next one. And this actually means we can.
Like you have half a minute.
I don't get you.
You have half a minute. You need to wrap up. We need to.
Yeah. Well, I'm being almost there. I'm not, so what we are beginning to get now is that the people that maintain the sunspot number and the group number are beginning to agree, and we can even agree with the cosmic wave people. And we see here the one, the minimum down there. So we have a fairly good idea of what solar activity has been. And here is the last 300 years, and we can relate that to TSI, and that's shown down here. So this is my view of what the sun has been doing. And based on that, we can then speculate about what happened during the one minimum, but that's a different issue. Okay, that's that.
Thank you very much.
Stop here. Okay.
Ilya, can you give us your point of view?
I will also show a few slides. Let me, do you see this slide?
Yes.
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 Okay. So I will be very quick, and I will be speaking only about sunspot numbers, so as it was posed the question, not about other indices. And actually, there are two indices called sunspot number. One is relative sunspot number related to or introduced by Wolf, with the famous formula as it's 10 numbers, the number of sunspot groups plus number of individual sunspots, and times K factor, which is a correction factor for the observer's quality. And the group sunspot number, which is just the number of group with some correction factor and average over many observers. The thing is that they are not equal to each other because of different formula, but this is minor. The most difficult part, or where the devil is hiding, is the normalization factor K, how one observer is connected to the other. And actually, at present, there are many sunspot reconstructions, maybe half a dozen or more, and they all fall in three roughly categories as related to the 18th and 19th centuries. These are so high series, which show very high activity during those centuries, as shown here with the green curve, which is Leif's series. Also, International Sunspot Number version 2 is quite comparable to that. Then low series, this is the dashed one, it's Hoyten-Schatten group sunspot number series of more than 20 years ago. And most of more recent reconstruction, I will say a few words later, turned to be moderate activity lying between these two. And the difference between these groups is related, as I believe, to this factor K, because the standard way is a direct proportionality. So what one observer sees, the number of groups, is directly proportional to the other observers with this constant factor K. But this is an oversimplified view. A more realistic view is and that's a modern approach, the AQT threshold. So the different observers have different AQT thresholds so that they see all sunspot groups with a size greater than some threshold. And this, as shown here, for instance, relation between the number of groups for the same days by Wolf's, reported by Wolf and Wolfer, the relation between them is not linear. So it's not just K. It's more complicated, and that's quite easy, because when there are larger number of groups, the groups on average are bigger. So even observer with this pure instrument can see them. And this is not linear. And the thing is, when you apply linear, you tend to overestimate high and moderate cycles maximum as comparison to the acuity threshold. And basically all reconstructions based on linear approach predict high activity during 18th and 19th century than those based on acuity threshold. Now, can it be resolved? Yes, it can be resolved, but for that we need a raw Wolf data set. And now the work is going on, and this paper by Frederick Klett and others has been published just a few days ago. So there is a hope that we can proceed with that and reanalyze all data sets. Proxy data are not conclusive, and actually, if considering the accuracy of the proxy data, we are not able to distinguish between different reconstructions. And just for the summary, the main message is that presently there is no consensus. We have several groups of reconstructions, and they differ in the method of calibration, but there is a hope that we can merge with the new raw data being digitized and reanalyzed. So that was that message. Very brief.
Thank you for the nice summary. Since we are running a little bit late, I'm gonna go to the second question and open to the audience after that. And the question is to Judith, Matthias, and Natalie, but everyone is welcome. And what is the current understanding of how different the Maunder minimum was from a modern deep minimum, such as the one we have seen recently in 2008, 2009, and now, or recently? And can we rule out some of the old Maunder minimum scenario as unrealistic based on the recent model development and improved historical record? And I don't know who would like to go first.
I can start if you like.
Sure.
I'll try and share my screen.
And please continue with your question on Slido.
Whoops. Oh, actually, maybe someone else should go because I haven't haven't heard how to share the screen yet.
Matthias or Natalie?
Yeah, okay, I can start then. I just would like to make two quick comments about insights from radiation emission simulations of the solar photosphere. The first point I would like to address is the origin of the quiet sun network. This is a picture taken from the LIGHTS 2008 paper, which looked at the previous minimum around 2006. And if you have these deep exposure maps of the quiet sun, you do see still quite some network field in here. And the question is this part of the quiet sun, or is this still some remnant of the solar cycle? So the question is, would this stay during a grand minimum or would it go away? Now, the interesting thing is that if you look at dynamo simulations, that small-scale dynamo simulations actually can create such a network field. And I compare here two models. The lower one is a shallow model in a small domain. And then if you just patch them together, of course, by construction, there is no network field at all. But if you do small-scale dynamo simulations in a wide and deep domain, this one was 20 megameters deep, so you have a density stratification of 20,000, then you do get a network out of a small-scale dynamo. And it looks quite similar to what you see on the sun, and I leave this to you as a quiz to figure out which one is a quiet sun and which one is a simulation. So the takeaway here is, I would expect that the network, as we see it currently in the quietest sun we have seen during the recent minima would likely stay also during a grand minimum. The other question I want to address is, how much does the quiet sun contribute to TSI? What is the TSI sensitivity to the quiet sun feed strength? You can also address this with MHD simulations. You can create essentially a quiet sun simulations at different feed strengths and also sprinkle in some additional network feed. And then you can compute the TSI from these models. And what you find is close to linear relationship, how the TSI increases with the mean feed strength of these models in the photosphere. And the slope gives you something like the TSI sensitivity that turns out in these models something like you get a 0.14% TSI increase for every 10 Gauss of mean feed strength at optical depth unity. And that is a large number because it means if the quiet sun would vary 10% during a regular cycle, that alone would produce pretty much all the TSI variation you observe. So there's very little room for the quiet sun to vary at all during a regular cycle, which in my view makes it very unlikely that the quiet sun would become even quieter during a grand minimum. But it also tells you if for whatever reason you do not understand it does vary, there is quite some room for variation. You can kind of see how much you can go down the slope here. It would be something like a minus 0.6% would be compatible with the physics of the photosphere, but you would have to reduce the field strength pretty much by a factor of 2 or more than that. So these are essentially the two messages I wanted to share here.
Can I have another go? Sharing my screen. Oh. Okay. Okay, can you see that?
Yes.
Okay, so this is some work that have done recently with Yiming Wang, and it's impressed in AppJ. We ran a flux transport model back in time using as the input for the bipolar magnetic regions, the average of the higher and lower sunspot number groups. In other words, an average or moderate sunspot number as input. And this is the reconstruction of TSI that we made from that. You can see that from the Morna minimum to the present 2008 minimum, we estimate an increase of 0.07 watts per meter squared. This is a factor of maybe 3 less than our earlier estimates. The thing that we were able to identify is that, you know, a lot of us talk about what's the increase from the Morna minimum to the present, but you can see that the present minima has its own variability, as does the maxima, and there's a 100-year Gleisberg cycle in the maxima and minima. So the increase from the Morna minimum, for example, to 1964, which is near the peak of the last Gleisberg cycle, is larger. So when we talk about what's the increase from the Morna minimum, we need to specify where we're what time period we're talking about in the Gleisberg cycle. And the next, let me just show you in the question about how does how does our understanding now relate to past estimates? The estimate of that Yiming and I and Neil Shilley did earlier in 2005 shows a change from the average solar minimum to the Morna minimum of about 0.5 watts per meter squared. This is low compared to a number of other estimates, and our most recent estimate is lower still. This is our reconstruction shown here. The reason why the estimate is lower is that we found a different relationship between the total magnetic flux and the facular component of irradiance during the solar cycle versus from one minima to the next, so that the interminima changes have a different relationship with the magnetic flux, and that causes the the decrease to be less. So I would say that we can rule out most of these estimates, and that the increase from the Morna minimum to the 2008 minimum, for example, is less than any of these. So, thanks.
Natalia, can you say something? And if you like, then I'd like to open to questions.
I would also share my view of how I see it.
And people can raise their hand or put their question in Slido.
Yeah, you can now see my slides.
Yes.
Right. So the current estimates of the change in the total solar radiance and the Maunder minimum range from essentially no rise to about 6 watts per square meter. And the reason for that is that we basically don't have a suitable proxy for the evolution of the bright component, which is faculty large network, and which is the main source of the variability on longer time scales. So most existing reconstruction, they rely either on sunspot observations or on cosmogenic data. And they need to take some assumptions to how to derive the evolution of the bright component from the evolution of sunspot. And that is not straightforward because the relationship is not linear. Okay, I can change. If you look carefully, essentially, all existing models converge to the value of the change of less than 2 watts per square meter. These are now not all the existing models, and maybe not including the most recent ones, but you see here that most of them show the rises in the TSIs and the Maunder minimum of the order of 1 watt per square meter or even less. But the only exception is the ongoing debate on the model by Shapiro, and there is a more recent update by Gorlo, which suggests rise by about 4 to 6 watts per square meter. Now, all of those models, they need some assumptions, and they also, all of them with one single exception, need some scaling to the irradiance measurements. And there is currently only one model that doesn't require that scaling to the irradiance measurements, and that is the so-called Satire 3D model by Cochran Yeo. What she did, she used the 3D MHD model atmospheres instead of the usually used 1D models. Those have been tested against independent data, and they reproduce a bunch of other data. What you can do with them, so they are more realistic in physics as well. By using those 3D MHD cubes, she calculated HMI-like synthetic magnetograms and intensity images. And this, for the first time, allowed the direct link between the magnetogram signal and the brightness of the pixels. Now, by using that link, she could take then the observed HMI magnetograms and replace the magnetogram signal with the corresponding intensity spectra. So with by summing up the pixels, you end up with the irradiance on each given day when you have the magnetogram. And no scaling to the irradiance measurements is needed. As you can see in the top right panel, where the model is in black and the T measurements are in red, the model does an excellent job. The agreement is perfect. Now, unfortunately, this model cannot go back to the Maunder minimum because we need the high quality magnetograms for that. What we can do instead, we can try and get an upper limit on the changes in the Maunder minimum by making an extreme assumption that during the grand minimum, the global dynamo switched off. Then only local dynamo keeps operating, and then we use the simulations by Matthias that he just mentioned before. By assuming that only small scale dynamo is still operating, we could use the same model. So you have a disk free of all other active magnetic features, only the cubes for with the local dynamo operating. And then in the same way, we could compute the irradiance, the brightness of the sun during such a state. And for that state, the TSI level would be about 2 watts per square meter below the level of 2019, which is roughly here, with the uncertainty of 4.7 watts per square meter. Now that assumes that the local dynamo didn't change, as Matthias just said. If the reasonable estimate of possible changes was, I think Matthias said, like 0.1%, that would be maybe still within the uncertainty of this estimate. That this is an upper limit, assuming that the global dynamo really completely switched off. From the cosmogenic data, we have indications that it was not the case during the Maunder minimum. But we could see still from time to time some sunspots, and the cosmogenic data, sorry. The cosmogenic data even show traces of the solar cycle. So that during the Maunder minimum, this limit probably have not been reached. And that would mean that everything below roughly this line is
unrealistic. Yeah.
Should I say unrealistic? Thank you.
Yeah. No, you answered my question, because I was wondering how realistic is that we completely shut it off. And
so the rest remains the question, but everything below that is highly improbable.
Yeah, we had some sporadic observation of activity during the Maunder minimum.
We are also doing some work trying to recover, to get the information from the historic calcium 2K observations. This is done by Theodos STSW. He's done great work. It's still ongoing. Irradiance reconstructions. To do the really reliable irradiance reconstruction, one would need to invest more work to believe those data. However, the preliminary, our preliminary estimate. So he has collected the data from, I think, over 30 or almost 40 different data sets around the world, including currently like 300,000 different images. They need to be cross-calibrated. He's invested a lot of work to bring them into a state where you can use them for science. And these are historic photographs. You can't use them straight away. However, so using those data, he could produce a composite of the calcium 2K plush areas shown here, or maybe better, I show this one. So you see the composite is in black, and this is the uncertainty. Now, if you compare, and this is only plush, right? So if you compare the solar cycle variability with the potential changes from minima to minima, you can already guess that there is not much room for a strong secular variability from this.
Thank you very much. I'd actually like to open.
Sorry, if I can, I would.
Sure. Sorry, I thought you
continue. I would address your last point on the radio flux. Or with whatever you think I should stop here.
I think maybe this is a good place to stop, and I'd like to open some questions. I see Sarah had a few questions for the panel. Let me maybe put up the question again so people can see them.
Yes, actually, Calvin, would you please show the slide question?
Sure, I can.
Yes, so Sarah we have a question from Sarah. Sarah, do you want to unmute and ask the question?
Sure. Yeah, this was just sort of just an out there question. We have all these wonderful information about long-term records going back using ice cores or trees or whatever. I know there's some information in the regolith, the full moon, right, which tells you something about the solar cycle, the solar wind evolution. I'm asking you to speculate a little bit about if there's, since this is whole heliosphere and planetary interactions, is there other information that might tell us about solar cycle changes and how they've impacted other planets out there? If anybody wants to speculate on the panel and or the audience. And I pointed out, I don't know, we're going to Europa, right? What will we find? Feel free to mock my lack of understanding on these planets, but is there something out there? Is there more information to be gotten from the solar system?
So while people are speculating,
yeah, Janet and Eve, I think they want to say something to answer.
Go ahead, Janet.
Can you hear me okay?
Yes.
I think there's a group in the UK that's been trying to promote lunar sampling revisits and lunar coring as a means of getting at least the energetic particle radiation exposure history of a body that's been exposed throughout throughout the history of the solar system as a means of looking for things like super flares, at least, and the the escalation of activity going back in time since. I know we're talking about the solar minimum, but the activity is also a factor in this because some people think that maybe there was no solar minimum back in the early sun days. And the lunar record might be unique in that one can, in fact, bring back samples and do detailed dating and track analysis and composition analysis to the point of drawing out more than has been gotten from the meteorite record. So, I would advocate that they were returning to the moon. They were going to be roving all over it, doing all kinds of mining and exploitation things. We should be campaigning to do more heliophysics at the moon. And the history of the sun is a big part of that. So that's just my suggestion that we can make a thing of supporting some of these efforts to go back to the moon and mine it for heliophysics information.
Helia?
Yeah, I have thanked Janet for the introduction, but I have a kind of bad news about that. There is no time information from lunar samples. Lunar surface or soil and rocks work as a spectrometer. So we can estimate spectra of solar energetic particles and galactic cosmic rays, but there is no time resolution because it's not stacked record. It just stays there for millions and billions of years. So we cannot study solar cycles out of that, but combining different isotopes, we can and we do and we will study changes of the spectrum, so let's say of solar energetic particles over millions of years. Individual super flares cannot be resolved because of the same reason there is no time resolution, but the frequency can be roughly estimated based on that, and we have done this kind of work. As for Europe ice cores, this is a very nice idea, of course, but we need the ice core brought from there back to Earth and analyze. I don't think it can be done on Europe, but anyway, we can dream about that. But lunar rocks cannot be used to study solar cycle or individual events. There is no time resolution.
Leif, I see your hands up. Would you like to
Yeah, I would like to ask Natalie and Janet why in their TSI models, they only use sunspot data from the old sunspot number. So the sunspot number and the group numbers were revisited back in 2014, and we now have the new versions of both. And why are they not used instead of the old one, which has been discredited?
We actually we have tried all, and well, you do see some differences. They would roughly follow the differences between the various data sets, but the secure change would remain independent. So the change between the modern minimum and now is not sensitive to that.
And can I just say too, in our latest paper, we did in fact use the STSW version averaged with the group sunspot number, and the average of that corresponds really nicely with Ilya's sunspot reconstructions. So it's not, it's not true that we haven't used considered the latest sunspot reconstructions.
But you don't show it.
I didn't show it. I could show it.
Well, in your presentation, also in Natalie's, you only show reconstruction based on the old numbers.
There is a paper by Greg Kopp where he addresses exactly this point. And shows
yeah, they have it in the paper. Hanley, I see your hands up.
Right.
Yeah, I have a question for Liv. In your presentation, you showed this linear correlation between the sunspot number and the magnetic flux. I wonder how far it can go. Can it go to 0 and we say that the flux is about 9 times 10 to the 22? And is there any, or maybe it will saturate there? Is that still a valid range? And also, is there a way to compare with the dynamo models like what Matthias talked about?
Well, the comparison between the magnetic flux and the group number or sunspot number has one problem, and we have not solved that. And that is, we know there are systematic errors in the satellite measurements. So we don't know really where the zero level is. So part of the intercept, if you like, is due to noise, and we don't know how big that is. We can estimate it, but then you can always debate if the estimate is good or not, right? So, but it is at least my belief that the offset is not all due to noise. So I think that even at 0 sunspot number or 0 group number, there is still a sizable amount of magnetic flux on the sun. And the way forward there is to try to find a way of assessing what the zero level error is. And there is some work by Joseph Plowman and others trying to model that and come up with an answer. I think that is ongoing. But in my opinion, there is, for 0 sunspot number, there's still appreciable magnetic flux on the sun. Another reason why that is possible is that the cosmic ray variation also shows a solar cycle during the modern minimum. And so the magnetic flux on the sun has not gone to 0.
Thank you. There is a question from Sarah that is close to one of the questions we wanted to ask the panel anyway. She was asking what happens to the sun if we go into a Maunder minimum, what happened to the, if the sun goes to the Maunder minimum, what happened to the heliosphere? And we want to know what happened to the Earth climate. So I'm gonna pass this question to the panel. If we go to the Maunder minimum, thinking what you've shown us, the Maunder minimum is not very different from a longer standard minimum. What is our expectation in terms of the climate response and what the magnetosphere look like? And Hanli, maybe you want to start, and then we can circle the other panelists.
So are we now going to talk about the third question?
Yeah, the third question, but we expanded also what the magnetosphere would look like, not just the climate.
Okay. I don't know too much about the magnetosphere part, but I can share a few points or thoughts. Let me see. Can you see something?
Yes, we can.
Okay. Oops. I try to. That's okay. I don't need a full screen. So I can think of two aspects. One is I think in terms of the global mean climate near the surface, I would say we have a pretty good understanding of what's going on. We from previous studies of the last several decades, we know that the kind of the sensitivity is 1/10 of a degree Celsius per watt per square meter change of TSI. So I think the real uncertainty is really on the TSI level. I mean, we can blame or ask Ilya and Judith and the others for the exact number, but it seems we are converging now to about 1 to 2 watt per square meter. So then we can say that maybe that's what the mean change, the mean surface temperature change would be. I think so that part, I think it's we have a pretty good understanding. I think the interesting and still hard question is the implication for regional climate, and also that's quite a active research topic in recent years. I think the main reason is because the variability of the climate is so large that and the solar signal are usually so small, and it's very hard to kind of get a clear picture of the regional climate response. And maybe associated with that is another interesting thing is the role of the middle atmosphere, and the UV change. What's the role of the UV change, which is pretty big? I mean, 10% or more. And what's the role of the lower the visible IR change? So the top down and bottom up, and what's the relative roles? So I think those are the kind of interesting questions, and also that's kind of motivates our study trying to look at the extreme low solar conditions, and we learned some things from it, and I think we can talk more maybe in more detail about those results, but maybe I'll stop here and hand it to other panelists, and later we can come back to this.
Yeah, I open to all the panelists. Somebody wants to comment on what the Earth climate and magnetosphere would look like, or the heliosphere in general? What do you expect during the Maunder minimum? That would be different from a regular minimum, or how close would be, you think?
Well, the magnetosphere owes its existence to the solar wind, basically. And there's two things here. The magnetic field is important, but also the solar wind velocity and the dynamic pressure. Now, the solar wind velocity has a minimum. It cannot go below 250 kilometers per second, because otherwise the wind could not leave the sun. This has to do with the escape velocity. And so at the point where the wind takes off from the sun, the velocity has to be bigger than the escape velocity at that point, and that is believed to be around 250 kilometers per second. Now, with the space probes that are now getting closer to the sun, maybe we can get a better handle on that. But so if there was a solar wind at all during the Maunder minimum, the magnetosphere would look more or less what it does today. It may be a little bit bigger, in fact, because the dynamic pressure may be a little bit lower. But I don't think the magnetosphere would be much different. Another issue here, it has to do with comets. Do comets have an ion tail? And some say yes, and some say no during the minimum. And that again has to do with whether or not there was even a solar wind. If there was no solar wind, the comets would not have an ion tail. If there was a solar wind, then the comets would have a clear ion tail. The Great Comet of 1680 seemed to have an ion tail. How do you tell the difference? Ion tails are straight and the dust tails are curved, so you can do that. But this is still a research item, so it's hard to say, but that's one way to get at it. But in my opinion, the magnetosphere would still be there, would be not much different. So that's that.
So we have 5 minutes left. If there is any other comment from the panel, from the audience, any thought about what a Maunder minimum would look like?
Juliana, you posed the fourth question is the.
We can move to the fourth question.
Oh, okay. We're still talking about the third. Then I'll shut up.
We're still talking about the third, but if there are no more comments on this, we can go to the fourth one. And our first question was that some solar indices, they sort of saturate and sunspot number goes down to 0. So how they can properly model solar activity using these kind of indices in the upper atmospheric models. So how we can handle that part?
Can I share my screen to comment, to reply to that? Okay.
Absolutely.
Let's see. So can you see this?
Yes.
Yeah.
Yeah.
Okay, so we now have a long enough record. Well, it's not really long enough, but we have 4 or so or 5 cycles of, for example, the 10.7 centimeter flux shown here, and the facullar index, which is really in this case the magnesium index. And we can begin to separate out the relationships at the minima, which I've shown here in the dots, versus during the solar cycle. So it's the inter versus intra solar cycle changes. And you can see here that if you look at the intra-cycle relationship between F10 and magnesium index, which is what this really is, there's a different scaling than if you look at the minima. So it's about a factor of 2 different, which means that the minima are not going to scale the same way as the intercycle variations. So you can't just do a linear relationship between these indices. And this is the reason why in our magnetic flux variation simulations, we related the intercycle and the intracycle changes separately. What happens is the magnetic flux simulation shown here at minima has quite a factor of 2, almost larger variation than does the TSI. So I think the question about the indices is there's not just one answer. Here, I'll stop sharing now. There's not just one answer about, 10.7 a magnetic flux. I think it's a bigger question. All the different indices and all the different emissions from different layers in the solar atmosphere, I expect, or Eming and I expect, have different relationships among them during the solar cycle versus from minima to minima. And so we're just beginning to understand the minima changes, but it does appear that they're not the same as during the solar cycle.
No, that's very interesting. Ying, do you have a follow-up question on these?
Yes, we do have in the Slido, we have a question from Mary. Mary, do you want to unmute and ask the question?
Mary, you'll need to raise your hand so that I can find you in the list.
Mary?
I see her. I'll send her an invite. There we go. Mary, you can unmute.
Okay, am I unmuted now? Not yet. Am I unmuted?
Yeah, can hear you. Yeah, we can.
Okay, all right, good. Yeah, so there was a paper that is in press in JGR by Yermolov. I think I misspelled the name. And it has some kind of provocative title like the decline of the solar wind in the latter part of the 20th century. And this paper takes omnidata back to, I think, at least back to 1970, and shows that there has not been a significant decrease in the solar wind velocity, but all other parameters they looked at, including magnetic field strength, which certainly affects geomagnetic driving of geomagnetic activity, has decreased on average over this long time frame. So I encourage everybody to take a look at the paper. It should have been OEV. And I put the DOI there for people to take a look at.
Can I comment on that, please?
Yes.
Okay, I'll be very brief, but 1970 was the near 1964. It's the time period near the peak of the Gleisberg cycle. And I think what we're finding is that no matter what indices we're looking at closely, including the sunspot number, max and minima, where we see a decrease, a general decrease from 1960-70 period to the present, and that's basically the declining phase of the last Gleisberg cycle. So if you look from 1900 to 1970, you would be seeing an increase, which is the ascending phase of the last Gleisberg cycle. And I think there's converging evidence from a number of different studies about this. In fact, Alexander Rezmukin and Joan Fireman published in 2014 about this.
Mm-hmm. Leif, I see you have your hand raised.
I just want to point out that what you just say is just right. In fact, what we are, this decrease matches the increase we had earlier. So we are now right back to where we were in 1900.
Right.
So, and one could then argue that if solar activity has a great influence on the climate, then maybe climate should be like it was in 1900. Solar activity goes up and it goes down, and there's a cycle to it. And
it's not just the 11-year cycle. The 11-year cycle is modulated by the Gleisberg cycle. And I think we now have enough data, 50 years or so, to start seeing that we're in the descending phase of the Gleisberg cycle. And a real test for that is coming up, because the last two minima, the last two cycles have been the lowest in the last 100 years. But if they are being modulated by the Gleisberg cycle, which is what we expect, then coming up in the next couple of decades, we should see solar activity start to increase again as the next Gleisberg cycle kicks in.
Yeah, there are now a fair number of predictions of cycle 25 and maybe of cycle 26. And even, and the predictive power is not very great. The predictions range from almost more the minimum type cycle to one of the largest cycle ever. So we're sort of at the same level of expertise as we had in the previous minimum, which means we don't know. But
what I'm saying is that 20 years from now, if the polar fields at the next minima coming up are stronger than in the recent minima, that means that the next cycle 26 will be higher, and that means that we're in an ascending phase of activity. So if we can all wait for another 20 years, we can see if this theory works.
For the younger people, they can wait. Aldi, I see your hands up. You want to see your concluding things?
Yeah, I look forward to
Leif, I wanted to give only do you still have your handy? I see your hands up.
Sorry, I got my question wrong. I thought your question about to what extent solar monominimum can slow down the anthropogenic global warming question. I thought that's the fourth. But for that one, I just have a very quick answer. There's a good study by Miu et al. 2013. They imposed in the projection simulation of I think they used a future climate scenario for RCP 4.5. They imposed 50 years of a Maunder minimum with a drop of about 3.4 watts per square meter TSI. And what they found is that about 15 years after they shut down that, after that solar minimum ends, it goes back to the usual projection. So it's about 15 years for that kind of magnitude.
And that magnitude is an order of magnitude more than what we expect to happen. So I think if someone was to go into a Maunder minimum, it would be just a teeny ripple on.
That's right.
Like
it's
probably even less than the 11-year cycle.
That's right. Yeah, it's a few tenths of a degree. It's not a order of magnitude. I thought you said now the lowest estimate is 2 watts per square meter, right?
I didn't say that. I think the lowest estimate is like 0.07 or something, less than 0.1 watts per meter squared.
Oh, you mean percentage or?
No, watts per meter squared.
Watts per meter squared. I think we need to wrap up. I'm getting messages that it's time to break. But maybe we can continue the discussion during the break. People want to stay in, but we are officially in break now. Catherine, can you remind us what time should we reconvene?
Sure. Thank you, Juliana.
Yes, if you can return at 20 minutes after the hour for the poster session, and then our time, Mountain Time here, 10:20 to 12 p.m. Mountain.
Yes, I love that. That is a wonderful interface. Speaking of chat, as we're planning to do more, continue in this collaboration. Again, this meeting is not, it's the beginning. We're hoping that we'll be able to find a number of collaborative topics, and this will spawn a lot of exciting research in the next couple of years. So to facilitate this, we have formed, a number of you are member of Helionauts. Helionauts is a discussion board that is dedicated to heliophysics and collaborative research and communication. This was established by Raphael Atier, and it is a resource for our community. Raphael has let us set up a separate group for WHPI. Now, so a number of you have already been subscribed. If you're wondering, you might have gotten an announcement or a notification from Helionauts that those of you that are already members, that you've been put in this group. But not everyone is a member. So I am posting in the chat an invitation link. If you click on that link, you will be able to join Helionauts. Now, please don't share that with others, because we want to make sure that everyone on this channel is someone who's active in heliophysics, because this is something for our discussion purposes. So you'll be subscribed to the general Helionauts group, and also you will have access to the WHPI group as well. Yes, Sarah?
We welcome our planetary science colleagues, right?
Yes, absolutely, absolutely. Yeah, and so Helionauts, as long as you're if you're part of WHPI, or even planetary scientists in general, because it's the extended heliophysics realm. We have a couple of people in earth science area and astrophysics who are also member of Helionauts. So please feel free to join. It doesn't cost anything. It's easy. And then you can start a conversation. You can say, hey, I was interested in this. And has anybody else noticed this? Or is anybody else interested in working on this? So that is one of the elements. That is our discussion board that we can have. However, Sarah has been compiling, Sarah and Ian were going, oh, link gives an error-like message. Oh, that's bad. Christina tried to join. Can someone else try the link?
I just tried the link. It says here, I'll send you the what it says, the error, but it says no longer be redeemed.
Okay, I did not save the invitation. Oh, I see. Okay, you know what I need to do. Raphael will be so disappointed in me for being stupid about this. It said the max number of people that can use the link is 1. So now I will generate the link, I will save it, and this has a lot of people that can join. So thank you for letting me know. There. So that should allow you to join. So Sarah, oh, and Claudia would like a group picture. I think that's a great idea. So Sarah, I know that throughout the meeting you had mentioned and shown on a couple of occasions the assembly of the observations and models. Oh, Pete Riley, do you have a comment, Pete? Everyone, by the way, everyone here can unmute now. Everyone's been taken off of moderation, but we appreciate you raising your
Barbara,
hand. Yes?
I've turned off the feature to auto unmute. So if you need to speak, you'll need to raise your hand and we will unmute you.
Oh, okay. Oh, all right. Oh, sorry. All right. But Pete Riley, did you have a comment?
That was just with regard to the link. I guess I was the lucky one who clicked it first. So I got that first one.
the quickest.
Oh, Pete. Very good.
Okay. But I'm glad you're here. I'm glad you're here, Pete, because there has been discussion of how in the previous solar minimum, we simply used a ballistic mapping and the solar wind. And so one of the things that we'd like to tackle is how we will be doing more advanced connections of the solar features to the heliospheric and planetary measurements and measurements at Earth. So Sarah, did you want to
well, actually, a couple of things before. Sure. First, I would love to have Pete actually explain that a little bit more about the empirical models. And then second, I'd love to have Pete talk to us a little bit about the special journal issue. And then I'd like to turn into the discussion of like what you were going to ask me to do, which is to talk about the snapshot. But since Pete's here, let's grab him right now on those two issues. So how have things improved since we in whole Sun Month in terms of the mapping? Because I know they have. That's for you, Pete, and you're muted.
And I can unmute. Okay, so I guess probably a wholesome month. So a few years after that, we developed a technique that ended up being called the heliospheric upwind extrapolation, HUX. That's basically a compromise between doing a ballistic mapping and a full MHD solution. But in some ways, it's better than the MHD solution because the MHD solution could be wrong. So even though it's giving you an accurate mapping, it might be an accurate mapping to a wrong location because the model's getting some of it wrong. So this HUX technique basically takes the speed either at some outer boundary or some inner boundary. And we've worked out a simple way of doing it, even if it's on a trajectory of very variable radius like PSP, and can map it outwards. And the one paper just came out this year, Riley and Isan, and then there's another paper that we're about to submit, hopefully next week, Isan and Riley, that describes that. There's a Python package in there that you can download and you can just run yourself, and it's not much more complicated than doing a constant speed mapping, which is the ballistic approximation. So obviously I'm biased. I think it's a nice package and it's easy to implement, and it's not something that requires someone who's got experience with MHD models to use. Alternatively, we've got all of our MHD solutions online, and so if people do want to study the large-scale structure for the WHPI interval, we can provide that, and we can provide some tools to interact with them. We have a SciPy library that's available to look at the CoreHel results. The mass code that we've developed produces HDF4 files, so it can be a bit complicated to read them in. But we've got Python routines that will do that, as well as IDL packages too. So if anybody's interested, the HUX technique, if you're interested in that mapping, you can just Google it, probably my name and ISAAN in Google Scholar, and it'll pick up that paper, and you can get the GitHub repo for that. And the SciPy, again, you can download that from GitHub, and David Stansby has been the primary contributor, so we've been collaborating with him to develop those routines. So it's strongly coupled with SunPy and HelioPy in terms of its concept, and we're actively developing that. So if you do decide you'd like to use our data model results and you'd like to have some extra features, send me an email and we can certainly try to get them incorporated. So I think that's I guess enough to say about the mapping. If it turns out to be a specific questions and either you don't want to bother with our tools, you can call me or email me directly, and we can try and help you make the connections with different regions in the heliosphere. And Sarah, Barbara, you're aware of all the projects that we're involved with, so you know the types of data products that we can produce in general.
Yes.
Okay, so the second topic is the special issue. So Sarah had asked me to look into setting this up, and we did get 14 definite promises for papers based on the WHPI interval, and I'm guesstimating that there's probably another dozen papers based on what we've seen this week that people may want to contribute. So it would be useful to know who's not already contacted. Either Sarah or I would like to contribute to a special issue. And the special issue that we originally decided on was an AGU-centric special issue where the authors could choose which specific journal they wanted to submit to, and it would be collected together under the umbrella of space weather, because a lot of the topics aren't specifically space weather related. And so in some cases, it might be a stretch. Some people would rather go to JGR planets or space physics, or even reviews of geophysics might be an option. So we submitted the formal request to AGU in July, and we didn't hear back from them at all, except the same day they said, thanks for the submission, we'll process it. I asked Noah to get involved at the beginning of the week, and he submitted another request to find out what was going on, but we still haven't heard back from them. So it's at the moment it's a little bit uncertain, but I don't think that we're in a rush. Well, I think there's at least 2 people who've already written up the papers that they would like to submit as part of this collection. And so we do have to be a little bit careful about holding them up, but AGU I think should be accommodating and allow us to have a broad window to submit. So I was thinking that as long as we can get all of the relevant papers in by February, that might be a good time frame. So from now to February. If people need longer, but they're still very enthusiastic about submitting to this special issue, then we can propose an extension to that deadline. So I don't know how to proceed. Actually, I see there's a couple of comments here.
Yeah, actually, my question is related to what Mary just said. So if people like Mary who have a paper, if they submit it to a JGR, to a AGU journal, and then in the next week or 2, things get figured out about the special issue, it might be able to be directed into it. So we don't, if they can't wait, as long as if they are going to an AGU journal, they should be able to, even if it's space weather, even if it's JGR, it should be able to be funneled into our special issue if that happens sort of in the near term, right?
Right. I hope so. Yeah. All right. So this is a good point. Thanks, Mary. Noah's definitely on board, so he wants this to happen. So hopefully he can make sure that any papers that are submitted will be retroactively included. Could we get maybe a show of hands from people who have not already contacted either Sarah or me, but who would be interested in submitting to a special issue?
Yeah, so raise your hand in the
Yeah, it'd be good if you could raise it in the chat window too, Barbara Emery.
Good, I see some. Good.
I have a question. This is Christina. Can you remind us what is the focus of that special issue? Is it just WHPI in general? Because I know there's so many themes and campaigns and whatnot that this workshop has covered, and I feel like there's a lot of things covered this week.
Yeah, and I can come back to that. That's a good point, because what we want to do now is to kind of organize these thrusts, if you will. I don't think there's any limitation. If somebody's got a paper and it's relevant to WHPI, anything we've been talking about this week should be submitted to the special issue. But at the same time, to some extent, to kind of highlight the areas that were of particular interest will help all of these papers fit together better. Barbara, were you about to say something? I felt like
Me?
Barbara Thompson.
Or Emery? No.
But yeah, so in fact, that's the question, is what are these? Because I think we're starting to, it's pretty clear there's things that keep coming up. We had a very lively discussion about the high-speed stream periodic behavior and how it shows up all over the solar system. And that's an area where there's a lot of commonalities. There's the long-term variations that we saw there were some great posters showing, the variation throughout from the sun through the heliosphere to the planets over time. There's been a lot of things that have come up, I think, but maybe that's something we can talk about now. I mean, Christina, what do you think is the most interesting? I think it was Erica Palmera said yesterday, why'd you have a meeting about everything? It's kind of a meeting about everything. And as we go from whole sun to whole heliosphere, we're getting bigger and bigger and bigger. And so I think what it is you focus on the connections to try to get some sense of some sort of limitation so that it's not just about absolutely everything. And that could be a connection across time or space or both.
Okay, yeah, thank you, Sarah. I mean, very good.
I mean, what would you write a paper on? What do you think you're going to write a paper on, Christina?
You're calling me out. Oh my goodness. I mean, off the top of my head, I'd be interested in the planetary interaction aspect, right? Because I feel like the last collection of WHPI papers probably didn't have a whole lot of the planetary interactions part. So I'd like to focus on that. But the question is, I mean, I'm not quite sure what I would like to write about, but it probably something on, utilizing the MAVEN data set. I have to think a little bit more. I mean, so clearly I haven't started writing yet. So I have to think a little bit more and figure out if there's some gap in terms of papers that would be submitted to special issues that could be written by myself. But there's certainly folks in this current group of participants right now who can easily write up papers, from the Mars planetary interactions perspective.
Yeah, and I think that's ideally, it's an opportunity for us by gathering it in one umbrella. It means that the people in the different areas will see it in a way that they might not otherwise. And so definitely.
Exactly. Yeah. No, I see value in that. That's why I want to make sure, because I wasn't sure if it was just focused on the solar minimum period or whatnot, because I've seen the calls for that before.
Right. I think Carlos, you were saying something?
Ideally, I think it would be good if the papers are based on the presentations that happen in this workshop. So, of course, people can start doing new jobs or new things to present. But ideally, the idea of the special issue is just to bring whatever it was shown here during the workshop and to crystallize it into a paper. Into a special issue.
That's for sure. I don't think it limits, people are limited to that, but that's for sure. I noticed that Ed Tiemann is raising his hand. Is that left over from the paper, or do you want to comment?
Sorry, that's left over. I can put it down.
So Pete, in the past, what we've done is we've kind of kept a list of people's intended papers. So it helped. There's a couple of nice things. One is that other people can get inspiration for ideas.
So I have a Google spreadsheet with those.
Okay, excellent.
Yep.
Yeah, because it also helps the working group leads. They might have some good, everybody's been paying attention and thinking of ideas for collaborative work that might not have happened without WHPI. And so the working group leads will also probably be stimulating some of these ideas for collaboration as well. Yeah.
Can we share the list on through the main WHPI page, like you said, to spur inspiration, and so that people know to let Pete know?
Yeah, so from the people who put their hands up so far, the additional papers, one's from Jason, Christina, and Barbara Emery that I didn't already had, but I already had Mary's and Ed's.
I think Mary
I
was.
think Janet had her hand up too. I think Janet might have had her hand up.
Yeah, and I put up an additional one for my student, Emily Brago, who will also write a paper separately from mine.
Yeah, and let's see, there are only 28 participants here, and I think is more than half are not present, so they might be interested.
Good point. Yeah.
Oh yeah, they'll be
So maybe we could-
updates sent on the email
Yeah,
list.
that's what I was saying, like, you know, to make it public or at least like mirror a copy over or something.
So hopefully everybody on here is on the WHPI mailing list. So what we'll do is we will send another announcement out to the WHPI mailing list. Maybe Pete, as long as we get it official, as soon as we get it official, we can send another announcement out to them. We can send another announcement out to Solar News and SPA News once it's the issue has been formally accepted. And we can post an advertisement on our webpage saying that this is what's going on. And maybe provide, and with our WHPI mailing list, we can provide information for people who want more. I think the Helionauts will be a good forum for some of the more detailed discussions, like when people want to ask questions about how to do connect to somebody else's work, and then also the chat feature on the poster. So we'll try to send out an email after this that summarizes a lot of these opportunities.
We will send out an email after this. We won't try.
We will try to send it out in the next less than a week. That's what we're trying to do.
Okay, there we go.
But we will
so if you're not on the email list, please check the chat there. I posted the link to join the email list. I love the fact that we can do these virtual special issues. In the past, we've had to commit to a single journal, and we've also had to commit to kind of a single deadline. And so, you know, somebody who's ready had to wait months for the final paper to be in. This is great and versatile. Another thing that we're going to be posting resources on the portal is now you don't just cite papers. You can cite software, you can cite data sets. And so if you're providing, for example, Pete was describing that they're producing model data sets as well as software packages. Both of those, you can generate a DOI, or a direct object identifier, and that can be cited, and it's encouraged to do that, so that whenever somebody's writing a paper, they can track. You can track where your software or your data ended up, and where it was used. And so that will be a very useful thing for people to keep in mind as they prepare to share their work, and also to prepare to use other people's things. And I also posted a thing in the chat. The WHPI show and tells are really good tutorials. Now there was so Pete, John did a tutorial last spring. It sounds like some of the things you were describing have been added since then. Is that correct?
Yeah, I think John's topic was slightly different.
Yes.
If I remember, he was talking about the open flux.
Yeah, I don't remember the library at all. I think it would be good to have another one then. Because and this is the thing. So what I'm planning on doing is we will start to hold. There'll be a number of engagement things, but I'll be holding office hours. These are basically open times. A lot of you participated in the two I held last fall. They were great. They were, you know, a lot of people really helped us understand how to define the access portal. It also helped us understand how to set up the collaborative analysis environment. And so we will continue to do that. And I hope Pete and other people, if you have resources already for people to start using, it would be very efficient if we just pick an hour for people to come and attend and learn how to use it, rather than you have to do it over and over again. Does that sound good?
Yeah. Yeah, that might be very useful.
Heather, this might be a good time to transition to talk about some of because we're going to encourage that you all go out and you write your own papers, and and put those forward. We are planning at least 2 overview papers. Barbara and I did that last time. We'll probably do rock, paper, scissors to see who kind of leads which one. But what we did last time, and I think is a good sort of overview organizational thing, is to have one paper which is a snapshot paper, and one paper which is more kind of talking about the evolution over the entire time period. And if you let me share my screen, I'll show you what I've started to put together, and I'd love to get other people to volunteer to join. So what we're talking about doing is okay, so this is a Google spreadsheet. This is what we did for we had a paper, and in this paper we picked one rotation. I'm going to have to do this. In this paper,
I mean, I have it already up if you want me to share it.
That's fast. We picked one rotation, and in this rotation, we took measurements showing one solar rotation, latitude, longitude, from the subsurface through the surface, out into the corona, and into the outer heliosphere, and then to the solar wind in terms of a time series, and to the upper atmosphere of the Earth and the radiation belt. So we followed essentially that whole time period. And that's what I mean by a snapshot. And so here, oops, I need this one. We've started putting together a spreadsheet, and we could have lots of people involved, anybody who's willing to help coordinate this. We have observations of the sun and the solar wind at the Earth and at the other planets. We also have models, simulations, creating forward modeled observables. We have derived data products in all these regimes. And so the idea is to put them together into a side-by-side comparison. And I've started to put names of people. Here's the idea I have. And so Pete, so rather than having everybody independently working with Pete and trying to use his ballistic mapping software, and to remind you of how that works, let's say you have a magnetic boundary here at the sun. And if the field is open, it connects to the Earth and it creates a fast wind. Or in Mars, if there's a CME, it creates a forcing. And so it's that connection from the sun to the other planets in the solar wind. You can take magnetic models at the Earth or planet and map back to the source of the sun. And that's what this sort of a figure is trying to show. Where on the sun does the magnetic field line that you're connected to for the CME, for this, the high-speed stream, where does it map back to? This is a simplified version of what Pete was talking about, where you simply take the velocity at the Earth and you go back ballistically and then follow a magnetic field line in a potential field model. So that's what we're talking about when we're talking about mapbacks. So rather than having all the people from the different data and the different planets and everything work independently with Pete, although they certainly could do that for their own paper, for this snapshot study, the idea would be to have a couple people build some software that will take a simplified input and then create something that's completely the same for, well, it's the same for all of them. And that's what we did last time. So for example, what we did was when I had those pictures of we basically said, all the different observatories, send us your unwrapped sun, synoptic measurement, latitude, longitude in this format. I think we just used GIFs last time, right?
Yes.
Send us your time series from this, you send us something which is your quantity versus time. Give us an ASCII array. You know, so we basically said, this is what we need. And then we put them all in the same software to generate it. And so I think that would be the simplest way to make this kind of a snapshot comparison. So when I list your name, mostly you're on the list for either providing this little simple data set for your model or observation, or for reaching out to somebody else to get it and to help them do it. So right now, like Heather, you're on there a lot, but we would probably be identifying other people. So what I would like to do is share this spreadsheet with anybody who's interested in joining in this side-by-side comparison paper. And again, it can be, it's what we need are synoptic observations. So observations sort of over a time period during the WHPI time period. We're probably going to just pick one or two solar rotations. And right now, one of the things people are telling us is where they have data. So we can try to pick a couple with good overlap. So if you're interested, please either put something in the chat now or email me that you're interested. Or actually, I can just give you guys all, I can put this in the chat. And if you're interested, let's see if I can do this. You can follow this link and ask for permission, and I'll give you editing privilege, and you can go ahead and volunteer and add items, or you can just send email to me and we can work that way.
Sarah and Ian, you guys have done a great job putting this together so far. Yeah, I think you're exactly right, Sarah. We want to do it similar to last time. Pete was mentioning Python notebooks. We can make a template notebook for for the rotations, where the model, where we already have the correct model loaded, into that. Now, those of you who are farther out, so if you're the sun, you kind of know the time, the window. The farther out you are, the more you're going to have to do a larger interval, because it's not, you won't know exactly what time it is at a farther out planet or even at Earth that corresponds to those longitudes. And so you'll want to go a week, 2 weeks, or even 2 weeks after the end of that rotation to put that to create that data array. And then once we have a template notebook, you can put it in ASCII, JSON, anything like that. We should be able to then generate them in a consistent manner. It's even easier than last time, you know. So and then IDL or well, I mean, once you produced it, we'll do it in Python. But you know, the tools. But we can also work on making a template in IDL as well.
And I would love to get a volunteer from somebody who works in Python who will actually do this, because I don't work in Python. I agree we should do that. So I'll help with all the organizing and getting people to present their, you know, get their stuff in the right format. But somebody else probably will need to do that coding.
That's a very good point, Sarah. I think Ian and I have been kind of working on setting up the system. We would very much appreciate volunteers to help with managing the collection and the access of different resources. We have the GitHub site, and we will have the cloud, which will have external access to it and executable things. But I'm Solar. I'm going to need. I would be very happy if someone who has experience in manipulating data sets would volunteer to also be on the core group of people who are responding to create the resources for the resources for WHPI, especially in the creation of this atlas or this snapshot. The snapshot is kind of like an atlas of the sun and all of the associated things, just to put it in context to see how they look for these different rotations. And I think you're right, Sarah. We can do multiple rotations. Once for a lot of these, once we've got one, it's not too hard to generate other ones. So just depends on what's available at the time. Excellent. Okay, I can see people putting things in here.
Yeah, if you has any, well, actually, I'll check my mail. People may have asked for.
Yeah,
I think I made this world editable just with the link, so I don't think you need to ask permission. It's true. I see a lot of anonymous animals now. So if you follow that link, and we just started doing it, but you can add cells to this, for example. And if you're kind of willing to stand up and be the one to call on, and again, don't be put off if somebody else has put themselves in a cell. Often there's more than one person needed, and often there's one person who's volunteered for 6 things. So we need more coverage. So if you, I'm looking at this, and
Sarah, I was surprised you didn't put my name in all over that thing.
Oh, well, I kind of was assuming that you're my back.
Well, we like people to self-identify first.
We need some more Earth stuff. I noticed the ionosphere, aurora, thermosphere. It would be great for people to sign up for that. And again,
the Milestone team was very active in the original discussion of this, and so I'm sure that they will be. We can, when we open this up to the whole community, we'll get some really good contributions as well. Sorry, Heather.
Yeah.
Yeah, I was just gonna say I'm not sure who will be really interested in the New Horizons data, but I'm definitely gonna work on getting it into the system that Barbara is setting up to share the data set. So I'm gonna do that. And I'm going to try to do that for all the data sets I signed up for. But I think I'm going to be reaching out, see if I can find some early career people that might want to do, to lead some papers. I'm going to be looking to try to encourage more people.
Great idea. Yeah, and I'm a nightmare when it comes to coding. So anyone competent is encouraged to volunteer. Pete, that does bring up a thing that came up earlier in the week, which is that for as far as New Horizons, how far will the MHD extrapolation be able to connect to in situ observations?
We've only really tested so the simple extrapolation is it's a simplification of the momentum equation, and it's such a simplification, so it wouldn't include any pickup ion contribution. So I wouldn't have much faith beyond 5 or 10 AU. But we've never tested it. So even ballistic extrapolation outward seems to do roughly okay, but it's the scale. So as long as you're looking on larger and larger scales, then it seems like, you know, the streams are there and they do seem to roughly match up. But then when you get down to, you know, plus or minus a couple of days, maybe even to a week, as the further you get out, that the phasing is going to be off and maybe the amplitudes are off. So I would be very cautious about it. But since we've never tested it, I don't know.
Yeah, so I am going to reach out to take him. He has done some forcing on one of his models to input Omni data as an input, and he's been able to reproduce a fair number of the larger scale features in New Horizons data. So I was going to, he was one of the people I was going to reach out to, because I think he might be able
He's
to.
online right now.
Oh, okay.
Take
Oh,
care.
yes. Yeah. But another key thing we have going for us is that once you get beyond 10 AU, a lot of the solar wind has been so worn down that it's moving at a fairly constant speed, which means that Pete is right. He might be able to do a better job than you would guess.
Well, it's better than nothing, right? Tay, did you
I have
have
a question.
did you want to comment on this?
Yeah, I just want to comment on the modeling at New Horizons and beyond, because I'm about to submit a paper describing a model that includes pickup ions and turbulence all the way out to the termination shock. So
yeah,
I think I can contribute.
Can we put you in purple on the collaboration list? I'm pointing as if you can tell what I'm pointing at, but imagine I'm pointing at the screen. Can we put you in purple as someone to contact and would be willing to work with us in helping? Oh, great.
Yeah, and I will help Tay with New Horizons for sure. I've already been helping him, so I'll help him some more.
So let me make sure people understand what the point is, because we are kind of, anybody can edit, so we have to be a little careful. So what I've done is, and I don't know why we now have 3 on the left, but the column D, starting there, observation sun, and it's kind of going from the subsurface to the magnetic field to the corona out into the outer heliosphere. Then observations solar wind, and there's observations, they're not quite in order, we'll fix them later, but we've got observations in the solar wind at Mars, observations solar wind at Earth, observations in the solar wind at New Horizons. Then observations at Earth, these are things like radiation belt. This used to, I think, say thermos, I'm not sure what this used to say, but anyways, this is the Kip peak. And again, this has gotten a little bit jumbled because people are editing, but the idea was that there's observations, but then there's also derived data products. So at the Earth, you also have things like the thermospheric density, the auroral electron planet, power, the ion temperature. We have forward model. The distinction there is you take a simulation and you create something which is comparable directly to like the EUV emission. That's a little different than data product when you're pulling out, say, density and temperature from a model or from so that's essentially how we're doing it. Don't get too hung up on the this organizational principle. We're going to come back in and kind of clean it up. The key is if there's something that's in that is either a direct, photons or in situ sampling measurement, or something that is derived from those measurements, or something that is a simulation or a model product. Those are the sorts of things we want, and we want them in the regime of the sun, the solar wind, the Earth, and the other planets. And so find somewhere to drop a cell if you don't see your thing, and put the thing down and your name. And that's basically it.
Just put it somewhere.
We'll coordinate it. We'll figure it out, clean it up later. Does that answer, like Christina, you were asking about where to put stuff. Does that answer your question?
Yes, it did. Thank you very much.
Okay, cool.
Also, Mayasi says, is asking about interplanetary medium variability. So we're even being pushed farther out. If it's possible to do that, especially in the context of solar minima, how that varies.
Didn't somebody talk about, who was talking about Voyager and about some sensitivity even outside the heliosphere? Who was talking about that earlier this week?
Was that Elena?
Maybe it was Elena. Yeah. So
yes.
Yeah,
right. Yeah.
She's in a community that I'm just marginally a part of, or starting to get my feet wet into. And I wonder if there's any overlap with this community, or if there's any interest in that, and seeing how that changes with solar activity as well.
I think absolutely. If we can connect it to, because we have to, one of our questions for the end of this meeting was, what do we do next if we go from whole sun month to whole heliosphere interval to whole heliosphere and planetary interactions. I think we do have to reach out beyond the heliosphere.
You know, when we called it whole heliosphere interval, but it wasn't the whole heliosphere. You know, we didn't go out that far, but I mean, that's going out to the understanding the full context of the heliosphere it would be really exciting. Definitely.
So Pavel has been using New Horizons data to estimate the neutral hydrogen atom interstellar from SWAP data on New Horizons. And we're getting ready to process another year's worth of data. So I think he's probably going to do an update on that. But they have revised the estimate for the neutral hydrogen atom interstellar density that has been updated recently. So
I'd suggest an alternative. Instead of going bigger and bigger all the time, the danger is then we become bloatware, and what we should be doing is being guided by I think the underlying concept, which is we're campaign orientated, right? So as long as the different observations and the models connect things well together, I think it makes sense for us to use that, and we can become more thematic. We could pick physical processes or some other way of defining a new theme for the follow-on to this, but it should always be guided with a good connectivity between every single person in the room.
Yeah, I agree. I mean, I think that's what's kind of interesting about the heliosphere is that there may be connections even farther than we thought, and so that's interesting to explore. Sorry.
Well, it was me that was picking on Sarah, saying, "Why did you say like everything?" I'm like,
it was you, not Erica.
I'm like, I was like with you. I don't know how we're going to connect to this outer heliosphere stuff really well. It's going to be a challenge, like you said, to actually make a real connection. Yeah.
And one more thing, we need to leave something for the next iteration. This is the third one. So what will happen for the fourth one, right?
Well, there's always the
comparative
minimum means we're always looking for more data, another data point, right? We've only got 3. So there's always something new.
But 2032 is a long ways away. Juliana, did you have a comment?
Yes, I agree with Pete. We should be driven by what question we want to answer. But one thing is there is some push, at least from our friend with Parker Solar Probe and Solar Orbiter, that they would like to do this kind of campaign and coordination going into more active times. So I think a decision for our group, it won't be called sort of minimum initiative of some kind, but it's still related to using the experience and the work we have done with the solar minimum. Do we want to explore this more complex time? And so I think this is something that our community should think about.
And I think that what's different from the last solar cycle is that the last solar cycle, we did the snapshot or atlas, just showing the context of the different observations. And it was the largest assembly of coordinated observation ever done. This time is going to be a little different. We're not going to just be publishing the atlas, we're going to be publishing the software and the way it was done. And so this means that as we do this, as we tackle these difficult challenges of combining this, people will have the resources to also take that and adapt it for their own uses. And so this is something that will have even more legacy than I think the last one, because people will say, hey, somebody's already at least done this connection and combine these data sets. And so this will even have more power. I think one of the things when we first kicked off the colloquium series, Sarah and I talked about the legacy of whole sun month and whole heliosphere interval. And a lot of the collaborations a lot of my best collaborations in my career came from whole sun month. There's a lot of things that happened. I know, Pete Riley, I mean, this was the work that we did during whole sun month really kind of set the stage for a lot of our scientific emphasis over our careers. And our hope is that we'll be able to do that again by making these connections, by taking what we're really good at and giving us the ability to connect and broaden and collaborate, that we'll be able to set the stage for not just the solar minimum studies, but years of coordinated science and improved science.
And I think the key there is it's not we, it's the next generation. It's other people basically having the same experience of building a collaborative, using the framework of WHPI to maybe write a paper with somebody you would never have written a paper with before, and then end up connecting with them more beyond the solar minimum.
I'll be eligible for retirement before the next solar minimum, so.
I think that's a great point, Barbara, about the addition of the software and the tools that will allow people to connect the data, because as it's getting broader and broader, the data itself is getting much more complex. And so if you've got to juggle where do you get all the pieces of the data from and then how you interpret it, there's only a limited amount of time in each day. So I think that could be very helpful.
Yep. And with Jupyter, if you run them through a binder, meaning that you can execute them online, it means that everyone can run the code for themselves, access the data, modify the code, and so this becomes very straightforward. We're also working hard to see if we can support internal IDL operations. If not, then we'll just have to do do it in a form that shows the IDL and the result, but doesn't actually do the operations.
Mm-hmm.
Is anybody here? I know Python and IDL. Oh, Sarah's muted, but Python and IDL are the main ones. I think some people are also. We had questions about MATLAB as well. You know, I think it's becoming easier to combine things with different things, but there's still an impediment with the different programming languages.
Which is why if we do this snapshot thing, we'll figure out a way so that we can seriously just ask for data in a certain format and make it super easy for people to contribute. So the snapshot's an easy one. We've done it for the last two, so that makes sense to do have
you say point. Easy. No, it's an obvious one. It's not easy.
It's not easy. It actually is a lot of fun. I still have all the code I wrote back in 2010 or whenever it was for this, and poor Ian and Barbara Emery had to like dust it off and try to use it again. I actually got it kind of working, and now we're probably going to switch it all over to Python. So sorry, guys.
I have the stuff from 1996 when we did our maps in 1996.
But there are other things. And so what I figure is by starting with the snapshot, and then we start to see, and some people have different snapshots, different things. We'll also be looking at this kind of long-term, we've already seen some interesting things that are happening. The sun went from high-speed streams, coronal holes that were long-lived for 6 months. Then there was the CME period. Then there was the Mr. T coronal hole that established and was really, really geo-effective. And then, so there's different kind of highlight areas. And so there may be opportunities in each of these areas to kind of coordinate a group analysis. I'd be interested in hearing what other people who have been going to the posters and the talks, what are the subjects that you would love to connect with somebody else more to be involved with, either leading a paper or contributing to a paper or a research effort on? So maybe if people could just raise their hands. I mean, what are you going to kick yourself for not using this opportunity to reach out to other people on the call about? Anybody want to raise their hand? Somebody's raising their hand. Maj, go ahead.
Yeah, I think solar energetic particles and energetic neutral atoms are also things that I think would be interesting to see how their propagation properties will change throughout the solar system. And I think we have enough, we have the capacity to observe that, whether or not you have a direct instrument. For example, on the spectrograph that I work on for that's orbiting Mars with MAVEN, that's just noise, but it's there, we can see it, we throw it out. We can also retain it and study it and investigate it with a little bit more purpose, which I think would be interesting to do, and also to do something comparative with other spacecraft and see how that correlates with solar activity.
I second that, Christina.
Yes, because there's Parker Probe now. There is the understanding of the processes closer in is really important. And also energetic particles aren't just energetic particles. They're a way to sound out the heliospheric structure. You're talking to something remotely, right? And so they bring a lot of information, not just about the energization process, but the structures in which these energizing areas are embedded. So I think that's fundamental, really. I think that's a great idea.
And do we have those observations out like on the New Horizons as well?
Way before it hits L1 to enhance or
What was the question? I'm sorry.
Energetic particles and SEPs out in New Horizons.
Matt Hill has some energetic particle data, and he also can look at galactic cosmographies on New Horizons. So I can talk to Matt. Sorry about that.
Yeah, I think that's a great idea, Maj. A wonderful organizing theme. Anything else?
Put yourself in purple on the list.
Or, well, I mean, it's a different list, but I think I made a note. We will be cycling back to you.
Well, it might not. We could put another tab in the spreadsheet and
you're
do
right.
Science topics. Yeah.
Let's, or actually just in fact, we talked about the solar wind coming, but yeah, doing the same thing end to end, but the energetic particles definitely. And whether it's this paper or a different one, we can put it on the spreadsheet to kind of help us organize that.
I did put solar particle and GCR observations at Mars into the spreadsheet. I didn't quite know where to put that because solar wind, I wasn't sure if it was inclusive of particles or not, but I threw it in there.
Excellent. We'll figure out a way to coordinate that. But yeah. What else? What about the longer timescale? What about the comparative minima? Are there connections to be made with this group now about reaching back some of the stuff we had in our panel discussion or on the space age time frame?
Yeah, Mary.
Yeah, so I was really appreciated Judith Lean's comment about the Gleisberg cycle and the fact that we're, descending into the minimum of it. And it's very apparent, again, in this JGR article, analyzing the Omni data that I brought to people's attention and very relevant to my students' poster, and we'll talk about that. And so I really appreciated having someone like Judith who really takes the long view. So I think it's important not to just compare the current and recent minimum, but going back in time, and forward.
We already have a couple of entries in the data portal of very long, including cosmogenic isotope studies in the data portal, and so this we can really think our focus, last time and every time is to not just study minimum just for the heck of it, but to put it into context. Mm-hmm. And so, this is a good opportunity. I wanted to remind everyone that Erica Palmerio had a great suggestion. We've been having our WHPI colloquia about once a month on a Thursday, and Sarah suggested having this, we could have a monthly tag up just to see what people are working on, give news and things like that at the same time, maybe the alternate Thursday, at another point in the month. So I think everyone agreed that's a good idea, because this hour-long discussion has been extremely fruitful. And if we have it every month and everyone can build on it and things, then people who miss this discussion and we can work on new developments, I think we can keep things rolling pretty effectively that way.
Yeah, if I may, I'd like to suggest that we have like a coffee discussion, free format, but maybe centered around a topic. That may be more appealing for people to come and say, oh, they're talking about long-term variability over millennia. So maybe people like Judith Lane or Ilya will show up or live, or they're talking about CME and SEP events, or maybe not a very narrow topic, but at least something that can guide people that drop in and out. I don't know.
It can be the kind of things we've raised as these organizing kind of group things, like what Maj brought up, for example. I would be interested in learning more about what resources are available and what would we learn and how can we bring it in, how can we connect it to models and so on. So I mean, I don't think we'd want, I do think freeform is really important, but we could kind of focus it on a particular topic, as you say.
I think it's more likely that we get people this way, but sorry, Barbara, you have the hand raised.
What I'm interested in
I think we need a variety of things. Yeah.
Barbara,
Sorry, Barbara.
has her,
other Barbara. Oh, okay.
Okay, what I'm interested in right now actually is from Pete to give a brief tutorial on how to use the HUX, how to pick it up, how to use the Python, etc. Because I'm going to be probably trying to do that immediately for MapBack of the solar wind.
all right, Pete, you heard her. Any chance you could record us a show and tell?
Yes, absolutely. 2022 is looking good.
I know that feeling.
Okay, so you know, there's a number of thresholds to get over in terms of the mapping. So if you want to use this mapping in general, then I guess I could, I could develop a tutorial and show you how to do it, but then you'd have to go through, if you're not familiar with Python or some of the nuances of using that, that's a bit more difficult. We do have notebooks, Python notebooks in the GitHub repository, so you can go in there and just use those. So through a combination of those and just actually giving you the answer in a text file, there's lots of ways that we can get you the information that you want.
And I propose kind of an intermediate thing where we have, if we have a small group that wants to do sort of a mini hackathon, where the goal is to take something and adapt it or modify it in a way. If we have a couple of us meeting together, and you know, one lending the scientific expertise, one person lending programming expertise. I do have a Python programmer that's been hired that can support this.
Right. So in fact, and Barbara, we're gonna have to wrap up.
Okay,
quick, but Barbara Emery, I think that's actually comes to my point. You could, of course, be in that small group and be one of the people, but we don't need everybody to independently figure out how to use Pete's stuff. If we come up with a set of codes that a small group knows how to implement and then ask for the inputs from everybody else. So I think Barbara's right. Maybe the next step is to have that small group discussion about what codes we're going to use, how we're going to actually make them happen, and who's going to actually do the coding. And in the end, it may be her, Barbara's Python person. And then you wouldn't necessarily have to personally be the one writing those codes if that's the way it worked out. We can have that.
So I think it's not so much writing the code, all of that's already done. It's about understanding what the steps are. So it's more really understanding what the limitations are, because the code will run through and give you the output. So if you want to know what the Carrington longitude is as a function of time for Earth-based spacecraft or PSP or solar orbiter, it does that and it gives you the answer.
Yeah, but we want to make sure we do it right. So I think we'll set that up as a side thing, and anybody who's interested in being involved in that smaller group conversation should let us know. We need to wrap. We've got 1 minute, and we kind of, unfortunately, the problem with waiting to the end to do a picture is we've only got 18 people left. But why doesn't everyone turn on your screens and we'll get a diehard picture? Kelvin, can you take that picture?
Kelvin actually had to leave.
Okay. Do you want to take it, Catherine, or shall I?
We need a mosaic view of everyone.
Yeah, I've got everybody in gallery. I've got people in gallery. I can probably.
Okay, good. Mine won't let me show more than 9, so.
I'm seeing, I think, everybody. I'm seeing 4, 8, 12, 16, 17, 18. That is everybody, right?
Yep.
All right. Okay, so I think I can do it. So start smiling, everybody.
We have 3 more people to come.
Well, Showa and sorry, I said
Claudia and Taken.
If you're here and you want to turn your camera on, yes, thank you. Claudia and Tay, if you're here and you want to take your camera on. Okay, everybody, smile. I'm going to take a couple. Of course, it takes me a second to reset it. Okay, smile again. Okay, thank you, everybody, so much for coming.
Thank you.
Oh, and everybody, if you want to connect still on the poster gallery with the presenters, I just put the link in there again. Thank you.
Thank you.
Thanks for organizing.
Thank you.
Thank you.
All right.